Okay. So I think we should probably just go ahead and get started. Um, uh, thanks to everyone for attending our AMWG session. Looking forward to hearing lots of interesting talks. Just quickly, this is our code of conduct for meetings. I think most of it should be fairly self-evident. Just be constructive, etc. To ask, where am I? There we are. To ask questions, we ask you to please use the chat function. There will be a discussion period at the end of both sessions. And if presenters haven't already done so, it might be a good idea to send your presentations to Elizabeth Faircloth in case there are some technical difficulties. I also have a few, so I can also fill in if there's a problem. We'll have a wrap-up discussion between 11:45 and 12:30. Obviously, the discussion is optional for everyone, but at this discussion, I would like to spend, we co-chairs would like to spend some time discussing results of a recent survey that we sent out on the possibility of removing some things from CAM to sort of reduce the workload on our software engineering group. We've gotten lots of feedback, and I think I think it would be very useful for people to stay and participate in this discussion. I think we need it's clear from the results of the survey we're gonna have to discuss things before proceeding. So I hope as many of you as I hope a lot of you will stay for this discussion. And finally, for anyone who's here in Boulder, we're planning on having sort of an informal in-person networking at the Southern Sun, beginning at around 5 after the poster session. So it would be great if anyone here who's in Boulder would join us, and I hope to see some of you there. And I think that's it for the introduction. I think we should just go ahead and get started with the talks. So
okay,
I'll stop sharing.
Yeah, so I'll take it over and just provide a couple reminders for the speakers. So in this first session, we have 6 talks before our first discussion, right before the coffee/bio break. Just a reminder to the speakers, you have 15 minutes total. So I'm probably going to turn on my camera and interrupt you at 14 minutes because we want to stay on time, and it's going to require a little bit of, there's always the transition cost going to speaker, as well as maybe the time for a quick clarification question. So heads up, so try to keep it to 14 minutes or less, but preferably even less to have some initial questions. So to get us started, I see that Rich is here. So our first speaker today is Rich Neale. So Rich, if you want to start sharing your screen. So Rich is going to talk about the climate response of convective parcel modification in CAM. So take it away, Rich. Oop. Your screen there. Let me try it again. Okay, now just swap display real quick in the upper left. All right, perfect. And then you're on mute, so.
Sorry about that. Too many screens.
All right, you're good.
All right. Yeah, thanks, Kevin. Julio. So hopefully this will just serve as a kind of wrap up to some modifications we've recently been implementing in the model. And ostensibly it's to address some of the problems we've seen when we've increased the vertical resolution. And in particular, working towards a target workhorse model up to 58 levels, and that's 10 levels in the boundary layer. This was prompted by some sporadic crashes we'd seen and actually quite a significant loss of skill in the simulation. And those crashes, we sort of put an ad hoc fix in, but we went and took a better look at what was actually going on and trying to understand what these sensitivities were. So that will be the first part of there's kind of the 3 purple lines there. I'll talk about this initially, and hopefully that'll kind of be done for the implementation. A little bit of a mention of its performance in AMIP and how we had to make a fix over land. And finally, if I have time, I want to talk about another problem I think that may need some addressing with respect to deep convection. Oops. Okay, so when we looked at the implementation of these extra vertical levels, there's 58 levels, the surface level is much thinner now. I think it's of order 10 to 15 meters as opposed to 40 or so meters, the center of the level, with the standard 32 levels. And so when we looked on the right-hand side here, we can see my cursor's working. Oops, sorry. These are just simple single column models, Toga core, so West Pacific convective region. And we're looking at the convective heating on the right here that results from a deep convection scheme. And these are a variety of vertical resolutions. One extreme case here is 256 levels, but that's just to illustrate this surface level sensitivity. And if we look at this heating averaged over this Toga core period, we can see that, there's vertical distributions of heating. You can argue about the correctness of these different vertical resolutions. But one thing we really did notice is that surface level cooling, which was from downdrafts, really does start to get excessive with the gradual thinning of these levels that result with 58 and 256. And that's in the average, but on the left-hand side, if we were to bin all the kind of time periods of these single column model runs, we can see that with this PDF, this 256 level in particular, we're getting values of minus 60 Kelvin per day for a 20-minute time step. For the 58 level, which we're implementing for this workhorse, we're also getting values which we thought were excessive compared to the blues and the blacks here, which were the existing 32 level. 48 level is the same within the boundary layer. So we thought, can we implement something to offset this so we don't get such extreme values and this non-convergence of the response in the boundary layer? So what we looked at and found and tried to modify is this, the way that the parcel is initialized in the deep convection scheme, the ZM deep convection scheme. So on the left-hand side, this has been the case since CAN 3.5. Just to briefly summarize, is the scheme searches for the maximum where the moist static energy is, the maximum level. And that is almost always, in many, many circumstances, the lowest model level. And so there you see, could be the problem is that with a gradual thinning of these levels, particularly with 58 levels, one could see that it's always that surface level. And so there's a problem, as you'll see, there is a problem with that. And as you've seen already with the strong tendencies, on the right-hand side, we propose this modification where we introduce a vertical scale. In this particular case, it's half the boundary layer, and that determines the properties, and this is the moist static energy of the PBL, and the level at which the parcel now initiates, which is the top of this vertical scale. So in principle, this could be more insensitive to the vertical resolution changes. Just to illustrate how that changes the way the parcels are launched, we can see here, again, for the Toga core period, the solid lines are essentially this control of these vertical resolutions. And it's all, as I mentioned, it's always launched from the lowest model level, apart from a little blip here. But then when we implement this Parcel modification, we can see there's a much more dynamic level and Parcel property variation, such that during dry periods, essentially the convective cloud base is higher, the launch level is higher, and during moisture periods on the right here, it is closer to the surface, which makes a lot more sense. And with all the vertical levels, it's, for the most part, is kind of insensitive to that. And so going back to this PDF, if we were to now look at those different vertical resolutions with this implementation of this Parcel modification, we see the values are much weaker. They're not as strong in this near surface level, which we kind of hope for, and they somewhat collapse onto each other. So now it's determined more by this specification of this mixing length scale, rather than the fact that one of them has a 20-meter level near surface or an 80-meter near surface. So we jump to applying that in an AMIP simulation. So now, just to reorient you, on the left-hand side is from a few months of an AMIP simulation. So we have a lot of sampling available, so much more smoother curves. We have the 3 vertical resolutions standard here, 32 through 58, but we also have this modification. We're calling this ZM2 modification. And so we can see that in keeping with the, consistent with the single column model, we have somewhat stronger near surface cooling associated with the deep convection when we add these 58 levels, versus with 32 and 48 are pretty much on top of each other because their vertical level near the surface is the same. And so when we apply this modification, we move from the green to the kind of salmon color here. And you can argue we're overdoing it to a certain extent, but that is related to whatever we specify this vertical scale, mixing scale to be. But we are really doing away from these 20 Kelvin, 30 Kelvin surface. This is a daily value in this case, sorry. So it's 30 Kelvin for a day from the deconvection, which seems excessive. And of course, the surface doesn't cool by that much, obviously, otherwise, they get crazy mixing. And what happens is, this is all the same kind of tendencies, but from the club surface tendencies. So there's this large push-pull between these 2 different schemes here. So more broadly, when we think about the AMIP simulations, how is this performance? How have we changed the performance of the model more generally? Oh, let me just go to the bottom figure first, actually. So now this is a special diagram of what that mean tendency of that surface level is across the globe. So you can see this regional variation. And so, just L32, L48, pretty similar, of some mean magnitudes of order, 4, 5, 6 Kelvin per day. But then this initial implementation of 58, it's, up to 15, 16 beyond in the West Pacific there, Kelvin per day. And then when we apply this Parcel modification, we do see, amelioration of this impact. And again, if our target is to some extent the L32 and 48 lower level heating cooling tendencies, it's a little bit too much, but it's not clear that is actually our target. So, and this is changeable, and we'll investigate how this changes. Oh, and I just want to say that I did, briefly, it is very apparent that if you look at these root mean squared error statistics, increasing vertical levels is not a panacea for improving the simulation off the bat. Things get worse with L48 and also particularly with L58. And so, we made some erroneous implementation here, this red line here, and we were pretty horrified, but then we found that what the fix were, particularly over land. And we can see here that now with this 58 levels and this ZM2 implementation, we're comparable with L48. In some cases, the original tuned CAM6 L32 climate performance. So that's encouraging, and that's without any tuning whatsoever. So that's pretty encouraging. And just to iterate some of the kind of regional improvements, changes that we see. This is wintertime mean precip over the maritime continent, which has always been a problem anyway in terms of in the control version L32 over Guinea here, for example, and on some of the other islands. But bottom left here, when we did introduce off the bat the L58, we can see we've got strong, precipitation maximum right over the top of the island. And trim, trim is somewhat strong precip compared to GPCP, but even that doesn't show this, particularly over the top of the island's precip maximum. And then, this is the erroneous implementation on the bottom here. But then when we make the corrected implementation on the bottom right, we're really quite happy with the kind of level of precip biases, precip field and like smaller biases over the mountains. And really the biggest bias now is over the ocean, which has not really been the case before, just to the West Pacific there. So, 2 or 3 minutes left. And I just wanted to mention something related to existing problems, remaining problems, I think, with deep convection. What we've noticed in developing the vertical grid is that we're having trouble communicating between the free troposphere and the stratosphere in terms of things like the tape recorder, QBO, etc. And I went back and looked at what the vertical heating profiles of the model over different evolutions between Cam 3 and Cam 6. And these, again, this is a Toga core single column model simulation. On the left-hand side, this is the mean vertical heating profile. And you can see that, the kind of crown jewels of having deep convective parameterization and heating is that you get as Toga core shows on the right, you get these top heavy heating profiles, either for like kind of convective systems versus stratiform systems, 400 to 500 millibars. From Cam 3 through to Cam 6, we have made changes to this convection, which have degraded that significantly. And so now we're at a average convective height from deep convection of around 600 to 500 millibars. Now there's compensation in the upper troposphere from other moist processes, club, etc., microphysics. But, it is not that desirable. And I think, the first question is, oh my gosh, why did we do that? It looks terrible. But of course, there are other aspects that that were improvements. And this is the precip distribution, for example, during that Toga core period. And you can see the demonstrable improvements between Cam 3 and successive models. And things like the MGO and Daniel cycle do improve. So this is not unknown, but this interplay between variability and like mean forcing. But one thing I've been investigating is how can we make convection deeper in the model? And this criteria of deciding where the top of convection is based on a buoyancy profile, and the way it's set up in Cam 6 is as soon as you hit a first level of negative buoyancy, that's the top of convection. And of course that, feels unrealistic. It should be a depth of convection that is a depth of, negative stability that should apply to that. And so just a quick summary of we've applied some modification based on the Parcel kinetic energy. And so that does not arrest the convective height until it's much higher in some circumstances. And just a brief look here, 2 cases here now in this is Southern Great Plains on the right type case, US case, summertime, and this is the Toga core case. And with that implementation, you can deepen, get a much higher convective maxima. And that does not seem to come, if I switch to precip here, at the expense of the simulation, at least in the single column model. In fact, there's quite a few improvements here. So the red is the existing and shallow convection, and the blue is the deeper. So I think that's just a plant a seed in people's minds that I think we need to think about this. So I'll, summary, 3 parts. We've implemented the Parcel modification to address some of these near surface issues. We've implemented this in AMIT, looks pretty good once we got it right. And then I really think trying to understand this lack of top heaviness is important for moving forward. At least with this convection scheme, we'll see what the EDMF implementation performs like. Thanks.
All right, thank you, Rich. We have time. If there's a quick question or clarification question, you can use the chat as mentioned earlier, or you could raise your hand really quick if there are any. Oh yeah, Julio. Oh, you're on mute.
You're on mute, Julio, if you're talking.
I can ask.
Yeah, I'm unmuted. Sorry. The error you showed that was 0.9 for L32 and went up to 1 for L58ZM2 is composed of lots of things, right?
You're talking about this one here?
Yeah.
Yeah. When you say composed of lots of things, no, this is just precipitation.
It's just precipitation.
Yeah.
Okay.
Sorry, globally, I did not mention that. Sorry.
Right.
Yeah. Just
I should have read that. Okay.
Yeah. No. Sorry.
Were there any salient features that contributed to the increase?
The decrease or the increase?
Well, there's
I think it's still over orographic features. I mean, there's still, over India monsoon, I think you can see a big jump, 1.64. It's just, it rains up against the Himalayas still, even with a correction, it's still raining quite a bit. So the 1.64.
Okay. Rich, I think there's another question in the chat, if you don't mind answering it in the chat.
I'll do it. Yeah.
To go forward. So we're going to switch to our next speaker, which is we're going to switch to hearing a little bit about the climate process team. So updates. So our next speaker is Colin Zarzycki, who's going to talk about the progress towards improving momentum flux parameterization in CAM. So yep, you're good to go, Colin.
All right. Well, thanks, Kevin, and thanks to the co-chairs for running this mess. So I wanted to just give a brief update on our CPT, which again is tasked with improving the representation of momentum flux parameterization, and we're doing so via club. So just a reminder, the CPT is jointly funded by NSF and NOAA. So thanks to them. Let's see, there we go. So this is the slide I always show, just kind of showing some members of the team. Just a couple quick notes is we've picked up a new grad student, Skylar. Chris has moved on to greener pastures, but Ben has started working at NCAR. And we are actually looking, Joao has also moved on to greener pastures at GFDL, and we haven't actually close this position yet. So if you have a PhD student who is looking for a postdoc out of grad school and might be interested in model development, please let me know. Again, I don't want to show stale slides, but this is kind of just a reminder of the two main improvements, at least on the CAM side, that are relative for CESM or CAM that we've been focusing on. One is adding a direct prognostic treatment of momentum fluxes into club. So rather than using kind of just an eddy diffusivity formulation for momentum fluxes, actually predicting prognostically these U prime, W prime, V prime, W prime terms. And then also modifying the way that club kind of essentially treats the vertical shape of turbulence. And it's using what we refer to as a regime-specific eddy timescale formulation, or something that we have affectionately known as, or started to refer to as the TAUS code, because we have been really leveraging this idea of an eddy kind of turnover timescale. And one thing that I think maybe scares people a little bit when we talk about making modifications or changes to club. So this is this new TAUS formulation we've brought in. Your immediate reaction might be, oh no, they've brought in more of those parameters that I still don't really understand what's going on with, things like the C2, C14. But I kind of want to emphasize that, in doing so, we've really designed, Vince and Zhen Guo and some other folks have been working on this code. We've designed it in a way that we're not really increasing the degrees of freedom in club. So we're actually trading existing parameters for new parameters that we think are more physically tied to kind of boundary layer processes, or shouldn't necessarily say boundary layer processes, but processes in the vertical that are parameterized by club. And our hope is that this does give us more control over momentum fluxes, and they're also more interpretable from a process-oriented standpoint. So on to the new hot off the press type stuff. So kind of probably the biggest outcome that we've had since the last time I've probably presented on some of this is that we actually now have this club, what we call Club X, or this code with those two improvements are now on CAM development. So they were merged in as of the tag 63059, which was, I think, about 3 weeks ago. And so big thanks to Kate Thayer-Calder, who did really the heavy lifting on this. This was much more challenging than any code I've previously been working with in terms of getting onto CAM development. But also Adam, Ben, Steve, Cheryl, Gunther, Vince, Jesse, Courtney, John, who are all people that at least commented on the pull request. So I apologize if I missed your name. So this was really like a big kind of aspect of getting this into CAM so we can start really evaluating what we're getting in terms of global climate. So currently our goal, and I'm going to talk about this in a couple slides, is really looking at retuning with the new 58 level model that Rich just touched on, as well as some of the CAM dev physics. And there's a possibility we'll make another merge in the late summer. We've been talking about separating maybe the damping of scalar fluxes from momentum fluxes. Currently, they're treated with handled with the same subroutine. If we partition them, that does increase club's cost. So we're thinking about the practicality of that. But some initial results show that maybe there could be additional improvements gained from kind of almost having essentially an if statement in the code on that, but not in CAM right now. So like I said, now with this code on CAM development, it allows us to not just operate in a sandbox. So we're kind of now starting to evaluate how these different modifications are impacting the global climate. So one thing my student Kyle has been working on is using short-term hindcasts to evaluate the sensitivity of some of these new components of club that we've added. So this club gamma coefficient has been part of club for quite a while, and it's been known by folks at NCAR and elsewhere that this really impacts things like cloud fraction in the atmosphere. But for example, we've introduced this new parameter that really controls turbulence and sheared flow. And what we found is that, obviously a term that impacts turbulence and sheared flow seems to have a relatively large impact. So if you look kind of horizontally on the stripe, this is the planetary boundary layer height, 10-meter wind speed. Anything that you see is a darker stripe means that club sensitive, perturbing that club parameter drives sensitivity in that output metric in the global CAM solution. So not unsurprising here, but this kind of gives us some indication of maybe which club terms are more important for various aspects of the climate system as we think about tuning and maybe kind of implementing all of these changes that some of which we're going to hear about today into something like CAM 7. And then with this information about sensitivity, which parameters are kind of controlling which aspects of the climate system, this kind of allows us to now start to think about kind of understanding and evaluating tuning. So this is one thing that we've been looking at, mainly led by the UWM group and Vince and his postdocs and grad students, but really a simple kind of almost like linear model of the sensitivity of these different fields, like things like stratocumulus, cumulus clouds, things like that, to these different parameters. So just an example here of how your stratocumulus might change if you change C8. And then you can actually use this to almost do this really simple matrix optimization to try to understand before actually running a simulation. This is the type of thing that you could kind of almost like code up in MATLAB, run, and then try to predict maybe what the CAM output would be. The kind of tuning that I want to briefly touch on here, which we've been a little more focused on at Penn State, is a little more of a kind of physically based optimization strategy. We've been using this idea of what's called Nelder-Mead, and this has been sporadically applied for climate models previously. So the goal here of this is to be able to take a new configuration of club and push it into CAM, run these short-term simulations, and try to optimize the performance of that short-term simulation against some benchmark, whether that's satellite data, whether that's reanalysis data. And so this is just an example plot over here on the right, but what it's essentially showing is what we do is we kind of run a simulation of CAM where we hold these two club parameters that we know are really important for the boundary layer height, let's say C14 and CK10. We run this baseline configuration with our default values, and then we essentially start we blind this algorithm to what those default values are. And we say, okay, algorithm, you're on your own. We have no expert judgment. You need to figure out what those default settings actually were. And what you can see is that the algorithm, after a while, eventually hones in on this kind of quote unquote right answer. So this at least gives us some indication that maybe we can, for kind of small dimensional problems, use these type of optimization strategies to better understand what is going on with these new versions of Club, highlight where we have model errors and what processes are driving those model errors. So this is, I'm going to just show one quick top level example of doing this with Club. So one error we've had with CAM 6 and Club is we've had this issue where if we improve the sea level pressure fields via tuning, it degrades the surface stress fields and vice versa. It's been tough to really get an optimization of both of them. So we're going to use this Nelder-Mead algorithm, and we're actually going to try to minimize essentially nudging errors in the model. And what we find is that if we use this new kind of formulation of Club with the prognostic momentum fluxes and the TAUS code, this is the out-of-the-box CAM 6, so think CESM 2, and we use this Nelder-Mead, anything that's highlighted in orange shows a better global skill just using the atmospheric model working group diagnostics packages. And again, I'm not really going to spend a lot of time on this and get into the weeds, but essentially we see a lot more orange than we see a lot more yellow over here. So that at least Club X with this tuning shows some positive potential and in terms of improving some of the biases in the climate model. We can also use this tuning for interpretability. The nice thing about this is with the prognostic momentum is we can essentially look at, for example, what is Club X doing differently than CAM 6 that provides better global skill metrics. So one thing we find is that this red here is kind of what Club X wants to do with this optimization. Blue is this CAM 6 out of the box. These are just profiles of effective diffusivity. And really what we've been finding is that we think that the CAM 6 out of the box configuration is just too diffusive, and that momentum diffusivity is just spread too deep through most of these layers. Although this does have fairly large regional sensitivity as these plots outline. And then the final thing I want to highlight before I wrap up here, because I see I have a couple minutes left, Skylar, one of my new students, has been looking at Eureka and atomic field data. So for example, what we can do is we can run these hindcasts with this Club X configuration with the prognostic momentum fluxes, and then look at how the flight level momentum fluxes vary from what the model is simulating kind of in hindcast, capped mode, whatever you want to refer to that as. And one interesting thing we found is that there's this pretty systematic offset where CAM wants to have higher zonal momentum fluxes and lower meridional momentum fluxes. And we think this is likely tied to errors that we've already been observing with wind turning in the model. So this is a slide from Kim and Gunilla at Stockholm University. But essentially this black curve here is where we want to be in terms of observations of wind turning distributions. And this red curve is essentially what we have for CAM 2, CAM 6 CESM 2. So we think there's plenty of room for improvement with regard to wind turning, Ekman spiral associated with momentum fluxes. And then last slide, I promise. And this is one thing I do think we need to talk about in the AMWG. But we've noticed that with the higher vertical resolution, as well as these less diffusive configurations of Club, we've started to see a lot of noise crop up, especially over land in terms of things like the 10-meter wind speed field. Julio showed a slide, I think, in the AMWG update that pretty much showed these are like time series of single column models where all this fuzz is essentially these rapid time step to time step oscillations and things like the 10-meter wind speed. The physics reordering seems to help. If we apply a 1D stress update in the Club loop, that helps, but neither of these necessarily completely solve the problem. So I do think we need to think about discussing potentially tighter coupling between things like the land and the atmosphere as we move to higher vertical and horizontal resolution. So with that, here's my summary slide. This code is now all merged onto CAM development. So I guess the big thing I want to say is neither option is on by default, but it's pretty easy to toggle for tuning and evaluation. So if it's something you're interested in, please let me know. I'm I'm happy to kind of work with you on maybe exploring this. The more eyes we have on it, the better. And then also, I will say that while we've been developing this, we have found that this is more stressful for the physics dynamics coupling. And I do think we are exposing some errors in the flux calculations, as well as some issues, truncation issues associated with long surface coupling intervals. And I think we want to think about that moving forward. So with that, I will wrap up.
All right, thanks, Colin. We have maybe time for a quick question, if there is any. Go ahead and raise your hand. But I think I don't see anybody jumping up. But we'll continue the discussion in the discussion at the end of the talks here. So thank you, Colin. So to kind of continue with the climate process teams, our next speaker is Joao Teixera. He's going to talk about the fully unified boundary layer and convection parameterization in global models, talking about some 3D results. All right, I can see your screen if you want to go to full screen mode.
Yeah, let me. I can't get to the full screen mode because of the bar up there.
I think if you, what is it, Control Command L? I always forget.
Yeah, if you could tell me what it is, that'd be great.
That's
because the
Command L.
bar over there, Command L.
Oh,
Wait, let me see. Command.
right. Probably. I'm coming from the Mac centric. I think it's okay. We can.
Yeah, it's
see.
a Mac. No, it's fine. I think I did it. Can you confirm that you can see it?
No.
No.
No, we see the same screen we did, which I think is fair if you want to just keep going with that.
What about if I move up and down? Do you see? You can see it moving up and down, right?
No, actually.
No?
No, we just still see your title screen,
Okay.
at least from my side, but
Sorry.
I don't know if anybody can hear beeping. I don't know if it's coming from my computer or if it's you. Yeah, okay.
No, it's not my mic.
Okay.
I have your slides, Joao. If you want me to show them, I can do
No,
that.
wait a minute. No, I can sort this out. Wait, just
Okay.
let me give me another.
Oh, yeah,
slide.
there you go.
How about now?
You must be
Can you
sharing.
see it?
Nothing changed in what I see.
Yeah, nothing changed over here.
What about now? Can I? No. So it's maybe I should share just this. Let me do this. Instead of sharing the PDF, I'll share the screen.
Okay.
Yeah, that I would do that. Yeah. So if you want to stop sharing and reshare the screen, that might work better.
Can you see it now?
Yes. Yep. And if you want to go to full screen.
Does it work?
Yep.
And can you see it moving?
Yes.
Okay, perfect. So, all right. Thank you
Yep.
very much. Sorry for the delay. No problem. I'll be on time. I'll stay on time. Thank you again for the opportunity to do this. Today, we're going to update you on some recent results from what we call a fully unified boundary layer and convection parameterization in CAM, which means a boundary layer, shallow convection and deep convection parameterization. So no need for an explicit deep convection parameterization in our simulations. This is, of course, done by a huge amount of people, in particular, thanks to everyone in this list, but Adam, Shannon, Michael, Julio, and all the others. We're a team funded by NSF and a little bit by NOAA. And let me start by moving to the next slide. This has been a goal of ours and many other teams in the country and in the world, which is to sort of get away from this modularity of parameterizations of vertical mixing that in the end just trying to represent the same physics. It just manifests itself differently, but it's all fluid dynamics with phase transitions and interactions with radiation. This is like a schematic that many of you have seen. This is from, I think it started with something with Arakawa, then Bjorn Stevens, and it's on the latest IPCC or the previous one. It's a schematic that tries to represent a lot of the important physical processes if you do like a cross section from, let's say, California to the ITCZ. And most models today, even today, often we'll have different routines to represent some of the physical processes that you have there in red. And we've been trying to sort of bring these things together. And we will today, we're very happy to show the first results from a fully unified turbulence and convection parameterization in CAM. So how do we do this? I will obviously be brief in this respect, but the essence of the story, and we'll show you a schematic that highlights that, is that club ends up representing sort of this double Gaussian mixing, while these multiple plumes represent additional discrete skewness of the subgrid PDF, and you'll see that in 2 slides from next. The multi-plume MF, and I have a very quick slide on that. 2 things to keep in mind. These are obviously multiple plumes, like the name indicates. We sample from PDFs of surface layer thermodynamic properties, and we use a stochastic lateral entrainment formulation that is partly based on turbulent kinetic energy. The way this is actually implemented code-wise and algorithmically-wise is with club is that we do it via the 5-diagonal prognostic solver that exists for solving mean fields and turbulent fluxes that are solved simultaneously within club. And so what we do is that we add this extra explicit right-hand side term that you can see in this equation based on the multiple plumes. So directly affects the equation for the mean flow, for the mean field. It indirectly affects the fluxes as well, because this is solved simultaneously. Now, the multiple plume is something we've played with and worked with for quite a while, for about 10 years now. The idea is that you have multiple plumes that start from the surface or near the surface. We represent the PDFs of the surface layer thermodynamics. We sample that PDF, so some of these plumes initially, when they initialize already, are more energetic than others. And at the same time, they will go and encounter different levels of entrainment and different numbers of entraining events. And this is basically partly inspired by a paper by Roms and Kwang, but has a bunch of modifications recently. And the 2 main messages here, I think the main one is that because we have multiple plumes, we are able to have different types of convection coexist in the same model grid box. So you will have dry convective plumes, you will have shallow convection, you will have deep convection, depending on the environment. There are no trigger functions or sort of partitions or anything. They can all exist in a friendly way within a grid box. Now, another aspect which is secondary but relevant is that the total updraft area and the properties, the updraft properties, are basically the sum of the individual updraft areas at a certain level, right? So some plumes will live up to that, others will not. Now, let me just show you, there's a very nice paper led by Michael White. I think it either is about to or was already published in Monthly Weather Review. The review process is finished. It covers essentially single column modeling with CAM, with SCAM for shallow convection events. This is just one example. This is the BOMEX case. On the left, you have the liquid water. On the right, you have the updraft fraction or the cloud fraction. And what you can see is that the black line is LES, blue club, red club MF, which is this merging of club plus MF that we've constructed. And then we kind of decompose into the club partition and the MF one. But essentially what you can see is that there is an extra vertical mixing that is provided by the plumes, and that allows the red line to be closer to the black line. So for club MF is closer to the LES results. And one sort of simple way to see that is by analyzing this schematic that shows basically the perturbations at a certain level, in this case at 730 meters above the ground. That's about 250 above cloud base. This is just the perturbations in liquid water potential temperature versus perturbations in total water. You have 3 components in this image. You have the LES joint PDF. It's a histogram of a bunch of LES points in that level across the entire domain, every 10 by 10 meters or so. You can see the club joint PDF that is the sort of parameterized club joint PDF from CAM. And then what you can see is that that PDF really does not go across the space. Doesn't have the standard deviation or the skewness that is required to sort of mimic the LES joint PDF, but that the mass flux discrete plumes do occupy sort of a space in this diagram that shows that they have the thermodynamic properties on this sort of very skewed part of the distribution to do the right amount of transport and transport the right properties. Now, what we've been doing over the last 6 months, maybe to a year, but essentially the last 6 months, is to work hard on implementing this version into the 3D CAM and run a bunch of AMIP simulations, and we'll show you just a few results before ending the presentation. This is focused, so these are AMIP simulations of about 20 years, and none of these simulations has any explicit deep convection scheme. So ClubMF does everything from the PBL to shallow convection to deep convection. We focus first on PBL clouds. So there's this transition that many of us have been working on for a long time. We call it, well, it's the magic transition because that's the DOE experiment we coordinated, but it's also the GPCI, which is a previous, but think about a straight line across from, let's say, Long Beach or LA to across Hawaii down to the IPCZ. And on the top, you can see a climatology from satellite observations of low cloud cover. You can see the stratocumulus regions off the West Coast, and then slowly the amount of cloud just decreases as you move towards the ITCZ. And at the bottom, you can see the June, July, August cloud fraction at different levels from both club control and ClubMF on the right. The club control, by the way, as well as ClubMF, is based on the L58 version, not the L32. I'll show some L32 in the next plots, but this one is the L58, and that's basically the control we're comparing to. At the bottom, you see two different sort of remote sensing data sets, actually slightly different characteristics and resolution. But indeed, what you can see is that in this case, both the club control L58, not L32, would not be able to do this as well, as you all well know, and ClubMF seem to reproduce the behavior that you would expect. There are slight differences, but both of them seem to create stratocumulus in the right regions, and then the boundary layer gets deeper from about 500 meters off the coast to about 2 kilometers close to Hawaii, and with much less cloud cover, as you would expect, since you're entering the shallow convection region. So it does a good job in PBL clouds. I'll show you maps of that. This is the annual mean low cloud cover for this 20-year AMIP run, the observation. So I'll show you 2 or 3 plots that are very similar. They'll have 3 maps. At the top, it's the observations, level 32, L32 is the second one, then L58, both control, then ClubMF at the bottom. And you can see that the sort of the benefits that were present in the previous plot are here as well. The observations clearly show regions of a lot of low cloud, PBL cloud off the west coast of continents, in the North Pacific and North Atlantic, closer to the East Coast, and also all across the Southern Ocean. It's clear that L32 is not able to produce stratocumulus as it should. Both L58 and ClubMF are able to produce the stratocumulus regions with slight differences, but fairly effectively, I would say. And with the sort of the added benefit for ClubMF that it's able to produce clouds in the Southern Ocean and in the Northeast Pacific, the Northwest Pacific and Atlantic, with cloud cover that is less than L58 control and closer to the observations. Now, because we didn't have the explicit deep convection, of course, our main interest was recently to find out how does ClubMF respond to sort of the forcing of the Earth's climate in order to sort of be able to reproduce or not the characteristics of deep convective events. So if we look at precipitation, for example, so this is annual mean precipitation millimeters per day. Again, the observations levels, well, L32, L58, and MF, all of them seem to show patterns that are not too dissimilar, and that's very encouraging from our perspective because, again, we don't have explicit deep convection parameterization. We're allowing ClubMF to produce deep convective clouds when the conditions arise. But not only is ClubMF able to reproduce a climatology that is not worse than the one from the control version, it's actually able to produce rain in regions where it appeared that the previous versions had a little bit of difficulty at producing that sort of amount of rain. Now, this is not as conclusive as this is a 20-year AMIP run, but it's a very good sign. And then if we look down, and I'll finish with two very quick plots. This is high cloud cover. Let me move forward because I'm late. So let me finish with this one. This is outgoing long wave radiation observations on the top again, the same structure. And what this shows, as well as the high cloud cover and the precipitation maps, is that indeed CLUB-MF is producing the sort of the deep convective clouds that you would expect, that you can measure from measuring the OLR and measuring the precipitation in the high cloud cover, with sort of lower OLR in deep convection regions over the tropics, over the ocean, and over the continents, and then sort of very high values of OLR, very close to the observations in sort of the desert regions of land and ocean where shallow convection is prevalent. So last slide, very quick summary. Because I am late, I will let you read the slide. It doesn't say anything else that I didn't say in the presentation, but sort of the key message is that we were able to actually implement and sort of evaluate to a certain extent a fully unified PBL plus shallow plus deep convection parameterization based on this merging of CLUB plus NF. Thank you.
All right, thank you very much. I think in an effort of time to stay on schedule, we're going to move on to the next talk, but we'll be able to have a discussion more broadly here shortly. So our next speaker is Pierre Gentine, perfect, who's going to talk about atmospheric turbulence modeling using machine learning. So if we can see your screen, it's full screen.
Okay, great.
And we can hear you. Perfect.
Thanks so much. So thanks for the time. So I'm going to be basically following up on some of the talks that we were discussing earlier, and especially talking about how we could potentially better represent parameterization of turbulence in the boundary layer. And I want to acknowledge funding from our recent National Science Foundation, Science and Technology Center called LEAP, and also funding from an ERC called USPI. And I'm really representing here Sarah Shamek, who's a postdoc in my group, and she's been doing a lot of good work on machine learning and how we could use that at scale for different things for convection and turbulence. So really what we want to tackle here is trying to better understand and better also model the planetary boundary layer. And we know that there's actually very intense turbulence in the boundary layer due to updrafts and downdrafts and also to shear. And really what we want to do is trying to understand what is kind of the bulk average representation of transport and fluxes throughout the boundary layer. And throughout the talk, I will use standard notation. So the average here will be the slab average, and then prime will be the turbulent fluctuation. So that's how we actually notice the fluxes. So when we look at a typical parameterization, what we really want to do is we want to represent the flux. So let's say we want to look at vertical transport of potential temperature as a function of resolved variables. So that could be mean vertical velocity, could be potential temperature or turbulent kinetic energy here. And that's really kind of the art of the parameterization game. And there's been quite a bit of work on that in that space for many, many decades now, starting with the eddy diffusion model, which is the simplest way we can actually model turbulent flux, especially the vertical transport of turbulent flux. But very quickly, people realized that it doesn't really work so well in the boundary layer because it's actually very well mixed. So we know that we actually need to have this counter gradient term or something that would actually be able to transport over long distance. So there was quite a bit of work, first on counter gradient, then using this mass flux approach that Joao just discussed. And so kind of the state of the art right now is to use this so-called eddy diffusion mass flux approach, where you have a diffusion model and you have a non-local term here, very similar to what people use actually in convective parameterization as well. And that's really something we would want to actually try and improve upon. And we do know that boundary layers are actually very important for weather and climate forecasting for many different things, also for boundary layer clouds as well, but also for high impact weather phenomena in particular and organized severe thunderstorms. One of the issues when we start thinking about eddy diffusion and eddy diffusion mass flux is that even with the best tuning, so that's one example here looking at a large simulation where we took an example where we were trying to find the best sets of parameters that would work across many different simulations, so with various shear levels and various convective regimes. And typically what you will find is it can work in a particular regime, but it's very difficult to actually generalize to regimes that you haven't seen. So in that case, for instance, we had a fair amount of shear, and you can see that, for instance, the eddy diffusion mass flux, which is here the thin line, as compared to the large eddy simulation, has quite a bit of deviation, especially at the top of the boundary layer. And what's really happening at the top of the boundary layer is entrainment. And in fact, many of those models actually do not have a direct or explicit representation of entrainment. And that could be a major issue because entrainment is related to the growth of the boundary layer, but also to basically how much entrainment of scalars in particular and moisture in particular we would have in the boundary layer. So we are thinking that maybe we could actually try and find a better way, or at least starting to get a sense as to whether machine learning could actually be helpful to address that. So that's basically the objective, is trying to use machine learning to parameterize boundary layer turbulent fluxes. And we didn't want to use just a brute force perspective, but also trying to see what did we miss, for instance, when we are looking at, for instance, an eddy diffusion mass flux, taking that as the reference model. And really trying to get into the process level understanding and trying to think what are the key components of boundary layer turbulence across regimes, from more shear-driven to more convectivity or buoyancy-driven regimes. So what we did is we ran a bunch of large eddy simulations. Actually, now we extended the data sets from very shear-driven, so almost channel flow, all the way to very, very buoyant conditions. And that created a very large data set to work with to try and see whether we could actually predict the fluxes using machine learning. And as input, we will play the typical game of parameterization, where you will have the large-scale variables, so potential temperature, turbulent kinetic energy, but some other tracers if we wanted. And then we want to predict the vertical transport just due to turbulence of potential temperature, but also of TK if we had, say, a high order closure. Now, what we wanted to do is not brute force that. So in the LES, we have many vertical levels, and we thought we actually don't want to actually replicate that, because that would be very much like a brute force forcing, and we want to actually get something a bit a bit simpler, and something that would be like a lower dimensional representation of turbulence. So how can we kind of step back and avoid those many different levels, and having this massive and huge neural network in particular that will try and reproduce those fluxes, and that will have a really, really hard time actually generalizing to a context that it hasn't seen, or an application it hasn't seen in the training data. So what we thought is we could actually approach that using some sort of latent space, where we could try and reduce the dimension of the system, and starting on the turbulent kinetic energy profile, and then going into the fluxes and their different variables, and then trying to combine that. Okay, so I'll try to walk you through that. So the first step is you take the turbulent kinetic energy profile, again, many different levels, but you don't want to reproduce that necessarily, right? I mean, you want to have some sort of embedding of that, something that's way simpler than that. And so that's what Sarah did. She actually created this latent space, and I'll explain in a minute what it represents, but it only has 4 dimensions. So it's a very compact representation of turbulence and turbulent kinetic energy. And you have what we call an encoder and then a decoder. So think of that as a nonlinear PCA. It's very similar to that. And we are trying to basically recreate the turbulent kinetic energy again at the large scale. And you can do kind of the same for any other scalar you're looking at. So we also did it for momentum, but you can do it for potential temperature and any other scalar as you wish. And you can actually plug that in there as well. You have an encoder, so you're reducing the dimension of the large scale feature. And then you combine the TKE latent space with the variable latent space, decode that, and then you're getting your flux. So what this is telling you is that you reduce the dimension of the TKE, you reduce the dimension of your scalar, combine them, and then you can predict your flux. And you can actually do that in a relatively physically consistent way. So we can actually map that. So we first map the TKE. Then you could also make sure that you have, because you will have this latent dimension and you don't know what those dimensions actually mean. So we try to actually project that across different modes of one that would be more shear driven and one that would be more convectively driven, so that we can actually disentangle those modes. Think of that, it will be exactly the same as when we take a computer vision image and you have people with glasses or people with a beard. You just want to have beard or glasses, but you don't want to have those combined, right? Exactly like a PCA, you want to decompose those modes. So we said, let's try to project as much as we can on the shear mode, and let's try to project as much as we can on the convective mode. And that was a way to actually enforce those things. And we can do that again for when we use this strategy, we can do that for potential temperature, but we could use that for scalars as well, or for TK itself, right? So then we can always get the transport. And the main point being that here, the mapping is always the same. So the decoder is always the same. The only thing that's changing is really the latent space. So how we are actually reducing the dimensionality. But the decoding part is actually consistent, and we could use it for whatever we wish. So, it could be water vapor, it could be some other tracer if you're looking at chemistry in particular. So it's generic. Okay, so how does it work? So in practice, when we look at TK, so we look at basically, we took the coarse grain version of the LES and we try to assess that at the kilometer scale. We could do that at multiple scales. So that's actually something we are trying to do now. And the main point being that across those different scales, we can, and those different samples, we can actually do a very good job. So when we look at all of those samples, so those are just examples, but they are very typical of what we are seeing. We can capture a lot of the modes of variability of the TK sample in the boundary layer. And here is a summary of the result from the encoder. And the spread here is showing the variance. And you can see that the model is actually able to also capture not just the mean, but also the variance across those many different samples. So it's kind of good news because it means it's not the model is not very static. It actually can represent a lot of the variability we are seeing in the boundary layer and across the different samples that we are seeing and basically the spatial heterogeneity that we are seeing. So that's good news with it. We can look at the heat flux on the left-hand side. So what is the quality of the reconstruction? Again, only with a dimension of 4. So we only have 4 modes, that are trying to reconstruct that. And again, we can see that we are doing a very good job here across the different samples. And I want to emphasize here that those samples actually span a really huge diversity in terms of shear conditions and also buoyancy and convective conditions. So this is, again, good news. It means we can really replicate what's going on, even at a very small scale. And if we look at the R squared here, that's actually the R squared across all of the samples in space and also across all of the simulations. So the accuracy is actually really, really high. And it means that we can really depict the kind of the essence of turbulence in the boundary layer. And that's for heat flux, but we could do the same for tracer, and we could do the same for the TK flux. And again, we have very good results across those many different samples. And again, we feel that we can really kind of reproduce the heterogeneity that we are seeing across simulations, across shear and buoyancy conditions, but also within a simulation itself in terms of the spatial heterogeneity. So really, that's something that for weather forecasting, we would think would work relatively well. And then we thought, can we step back and start disentangling what's going on in that latent space? Because it only has 4 dimensions. And so we could start and investigate what's going on in there. And when you start looking at the first 2 modes of that, what we are really finding is that, in fact, it's actually trying to depict the convective mode, so like a bottom-heavy type, so like a middle part of the boundary layer heavy profile, and then a bottom-heavy part on the right-hand side. And what we thought is that basically this mode here that we have here, which is the first latent space, is really trying to explain buoyancy. So that would be the equivalent of your mass flux component in the EBMF. And then this mode here is actually a shear mode, right? So that will be more similar to the eddy diffusion term, right? So it's really telling you that the latent dimension is really telling us more about the physics and how that's actually working. If we look at the higher latent dimensions, so 3 and 4, they are actually exactly explaining the entrainment. So they are targeting really the top of the profile. So that's really what we wanted, having also the effect of entrainment. And that's also true for the tracer. We can actually explain those convective modes and the shear mode, and we can actually start disentangling those effects. And you would recognize, for instance, if you worked on turbulence in the boundary layer, a typical convective mode for the TKE and a shear bottom one for TKE here. So again, this latent dimension is very physically based and it can really tell us a little bit more about the physics. And just to conclude, we can actually start investigating a little bit, what is that telling us, And so when we start thinking again about eddy diffusion, so it's again, you have a gradient, so the vertical gradient, and you have a coefficient, which is this K, so the eddy diffusion coefficient. And if we were to actually lump all of that together, so if we wanted to actually map that eddy diffusion, we would basically get those lines, right? So that's the projection of the total flux on the different eddy diffusion coefficient. And you can see it's kind of all over the map here. It doesn't really tell you much, and there's quite a bit of discrepancy between the shear case, the very convective case, And really, we don't see any convergence between those lengths. Now, if we use the modes that I just told you before, like the first mode to the first latent space, and now we project onto that first latent mode, we can see that there's a collapse actually of all of the eddy diffusion flux. And what this is telling us is really eddy diffusion is really due to shear, and that's why there's actually this collapse across all of those modes. And it means that we can really start understanding what is the physical process at play in every single one of those latent dimensions. So again, the first mode is going to be more like a eddy diffusion, and that's more shear driven. And then we could constrain that. So very quick summary. So it seems that machine learning can really help. First, better understanding physics, but also predicting with a very, very low dimension turbulence in the boundary layer. And one thing that became very clear is that we really need to also create this dialogue between domain knowledge and machine learning, because informing the retrieval with physics guided, such as projecting on a shear mode or convective mode, was really, really important as a way to actually represent those different things. And we believe that we really need to work at the interface between the two fields. And the next step will be to integrate that in CAM. So that's what we are expecting to do next year. Thanks.
Great, thank you, Pierre. We have, if there's any quick question or so, feel free to raise your hand. If not, can continue to interact in the chat. So just as a reminder to speakers, as you finish your talk, there are questions coming across in the chat. If you could refer to them. But maybe to stay on time, we'll move to our next speaker, who is Arti Jadav. Is going to be speaking on the implementation of secondary ice production mechanisms in the single column model SCAM version 6 with results from MC3E. So if you want to, yeah, oh, perfect. Do you want to go to full screen mode, Arti?
Yeah. Okay.
Perfect. We can hear you, and everything looks good.
Okay, yeah, I'll start. So today I will be talking about the implementation of the secondary ice production mechanisms in the single column version of the model. And yeah, this is with Arti Jadav, that's me, and I have done this project with Deepak and Juan. So our objective for this was to have a better treatment of ice and the deep convective scheme, and for this, the approach was to add some secondary ice production mechanisms in the CESM model with the help of the single column version, which is good for the model development. And our implementation was it was based on the hybrid bin bulk scheme, which is based on the Phillips paper, the Phillips et al. Paper 2007, 8, 17. So this hybrid bin bulk scheme means that we, during this processes, we represent the total number and mass, but when the number and the number is discretized into the size bins, so that in the ice processes we have added, we get a better result. And we used the mid-latitude continental convective cloud experiment observation data for our validation. So I'll start with the cloud ice. In the deep convective clouds. So the ice is present in the cloud by initiation and multiplication processes. And this initiation can be by the aerosols which are present in the atmosphere, and this process by which the cloud ice is formed is called heterogeneous ice nucleation, in which the cloud droplets are and they become cloud ice particles through this insoluble aerosol species. And on the right side, I have a graph which shows that ice nucleating particles on the y-axis and their temperature dependency on the x-axis. So our model, and the black line is our model line, which shows a good representation with the observation, which are the blue dots. And also from this graph, we can see that below the minus 20 degrees, that the maximum aerosol aerosol concentration, which helps with this ice, cloud ice formation, is one is 1 per liter of air. And the maximum we can see is around minus 32 degrees, which is I think around 50 per liter of air. And the other process by which the cloud ices are initiated is the homogeneous freezing, which is just like you have this cloud droplets, which just instantly freeze to become cloud ice. But when we talk about the cloud ice, well, from the observations we have seen that these processes are not enough to explain the total ice we see in the clouds. So this means that there are other mechanisms which are active to produce the ice. And so to represent these mechanisms, we have introduced this the ice multiplication processes, and there are three well-recognized secondary ice production mechanisms. The first one is the Hallett-Mossap, in which the supercooled cloud droplets you have above, and all this is happening above the 0 degree level, which is the freezing level. So so then you have the supercooled cloud droplets. They rime on cloud ice and produce ice splinters. And this process is active in the region minus 3 degrees Celsius to minus 8 degrees Celsius. And then the next process is the ice-ice collisional breakup, which is the collisions between the different ice particle habits. And this theoretical formulation is based on the paper Phillips et al. 2017. And then the next process we have introduced is the raindrop freezing fragmentation. And there are two modes in this. The first mode is where the collision is between the ice particle and the cloud droplet, but here the ice particle has less mass than the cloud droplet. And the second mode is where the ice particle has a higher mass than the raindrop or the cloud drop. And this formulation is based on the Phillips et al. 2018 paper. So when we added this process, we saw a good validation with the aircraft observations during this MC3E campaign. And the black line here in this graph, the cloud ice concentration is on the x-axis, and the temperature is on the y-axis. And here I'm representing the total cloud ice, which is the addition of all the ice particle habits present in the clouds. And the black line is where is the one which shows the implementation we have had to the SCAM model, and which is in good agreement with observations. And to break down this, the total ice we are getting from different processes, I have done a budget analysis using the tagging tracers. And the tagging tracers I have used for the primary ice, and which comes from the heterogeneous ice nucleation and the homogeneous freezing and the three SIP mechanisms. And we can see that the Hallett-Mossap process, which is represented by this pink or magenta line, it's actually between the -3 and -8 degrees, and the most of the ice below the -36 degrees, it comes from the SIP mechanism we have introduced. And I'm sorry, I failed to mention this before. The homogeneous freezing, which is like where the cloud droplets instantly freeze, that is, it occurs above the -36 degree levels. But here we see that representation below the -36 degree. That is because of the downwelling happening in the cloud. And that is represented in the tagging traces we have introduced in this model. And this is a better budget analysis. So here I showed the total ice concentration in liters on y-axis, and the various processes attributing towards this ice. And here I'm talking just about the cloud ice and not any other ice particles. So we see that the ice-ice collisional breakup, range of freezing fragmentation are important in this representation of the processes, and also the homogeneous freezing. But yeah, again, and since we got this big number of the from the cloud ice from homogeneous freezing, because we are simulating the deep convective cloud, which goes above, which goes up to, I think, we have got up until minus 50 degrees Celsius. So yeah, that's why we have a lot of representation from the homogeneous freezing. And when we just look at the budget analysis below the minus 36 degrees, where the other processes are also important, we see that 84% of the ice comes from the ice-ice collisional breakup, and 2% is coming from the range of freezing fragmentation. So I think, so then it was important to have this representation of this ice multiplication processes and the deep convective scheme in the SCAM model. And our next step would be to have this mechanisms also in the stratiform microphysics of the model and do a global run instead of just having with the single column run. So we have the results from the single column run. So it would be good to have from the global run. Yeah. Thank you.
All right. Thank you, Arti. We have time for maybe a question or two before we move on to the next talk, if there are any. Let me check. Yeah. I see Adam raise your hand. Adam, do you want to unmute and ask it?
Yeah, sure. Thanks for the talk. Towards the end, you said that you wanted to maybe implement this in the stratiform microphysics scheme. So I gather you've implemented this in the ZM scheme?
Yes.
So okay. All right, I just wanted to clarify that. Okay.
Cool. If there are no questions, Arti, please just keep a look on the chat unless any come in. And then we'll move on to our final speaker before our discussion for the first half, which is Mike Pritchard, who's going to talk about Renaissance in cloud super-parameterization, emerging flexibilities for regionalization and machine learning emulation, opening new CSM science opportunities. I like the title.
Sorry for the mouthful. Yeah, can you hear me?
Yes, we can, Mike, and we can see the slides, so you're good to go.
Cool. Yeah. Well, thanks for letting me squeeze in on this session. I wanted to share my perspective on the super-parameterization feature in the CSM. So, I've been an avid user of it. I think it's really nice to have this switch that creates a diverse end member of CSM that has a radically different representation of its physics, just under the view that biodiversity is healthy for testing hypotheses about what controls global climate. And so super-parameterization is just this idea of embedding small samples of explicit high-res physics in a GCM by having a predictor-corrector relationship between thousands of small-scale models that make idealizations like two-dimensionality and periodicity in order to afford a representation of explicit cloud physics emerging from appropriate governing equations like the anelastic system, so explicit moist convection. And it also turns out to provide nice low-dimensional arteries through this predictor-corrector relationship for machine learning, which I'll speak to. So philosophically, the appeal is just to reduce the number of parameters, the number of interacting parameterizations, to avoid making assumptions about things that are hard to think about, like convective organization, to allow microphysics to interact more naturally with the explicit updrafts that it tends to be formulated to interact with. And a consequence is a lot of freedom to vary the GCM vertical resolution in ways that don't produce major effects, and vary the horizontal resolution, so more scale awareness. So this approach has been used for 15 years, and in the last decade, it mapped out a lot of issues about the storm resolving era ahead of schedule. So, insights in how the Madden-Julian oscillation works and its climate sensitivities, and insights into how explicitly resolved deep convection is sensitive to warming, including regional extremes and mesoscale convective systems. Of course, now global storm resolving models handle that more elegantly, but only for those who have access to huge computational resources. And I want to suggest that this next decade, more flexible MMFs can democratize that global storm resolving simulation, and also especially allow us to begin to penetrate the sub-kilometer turbulence frontier ahead of schedule. So on the first point of flexibility, I'd like to show an example. This is from a postdoc in our group who's been experimenting with making a regionally flexible super-parameterization. So normally super-parameterization is one size fits all. You use the same cloud resolving model grid structure in every grid cell, but Liran here has decided to use the normal cloud resolving structure that resolves storms with 1 to 4 kilometer resolution in all the white regions of the planet. And in these blue regions, he's embedding much higher resolution, so 200 meter horizontal, 20 meter vertical, in order to resolve marine stratocumulus better. And so, if you try to do that globally, it's very expensive. Your simulations run very slow, and this is why Liran worked hard to try to fix this problem. On the left-hand panel, he's showing a theory he developed to predict the optimal processing scale as a function of the workload intensity, so the relative workload of the blue versus the white regions. Which obviously will scale with dimensionality of the cloud resolving model and resolution. And on the y-axis, the fraction of the globe that's covered with the high resolution. And if we redesign the MPI decomposition of the physics so that you can balance rate limiting cloud resolving models with one core with large groups of lower intensity cloud resolving models elsewhere on the planet, then you can unclog this load imbalance and get simulations that have a lot faster throughput and less expense with regionalized physics. So the right-hand plot is just sort of Liran validating his prediction of the optimal scale against measurements of the CSM that showed that it works. Now, you should beware that there could be problems at the artificial boundaries you've introduced between regions with different grid resolutions in the embedded model. And the right-hand plots here are meant to convince you that actually these are not large issues. The bottom plot shows you when we use high-resolution MMF globally, what the shortwave biases atop of atmosphere look like. You can see dim biases at top of over the stratocumulus zones. And the top plot shows you that you get basically the exact same pattern interior to the green contours, despite the fact that we've used a completely different, much coarser, less computationally intense grid structure outside of the green contours. So, this is just an example to point out that a regionally flexible super-parameterization is possible, that I think opens the door for lots of niche impacts or dynamic studies. Suppose you only want to study the tropical boundary layer in high fidelity and its interactions with climate dynamics. You could super-parameterize just the tropical rainforests and save a lot of computing power. If you'd like to, study the effects of Atlantic cyclogenesis on the eastern coast real estate, you could just embed very high resolution, large storm permitting domains along the corridor of cyclogenesis. Insert your interesting question here that deserves regionally variable resolution. So my own personal obsession is the boundary layer in the sub-kilometer physics, which should keep us up at night. We know that mixing between the PBL and the free troposphere is really important to equilibrium climate sensitivity, and that difficult to parameterize processes in the boundary layer mediate aerosol cloud formation that is at the heart of our largest uncertainties in climate prediction. This slide is just to point out that high resolution MMF can really change the representation of those physics. So here we're looking at the liquid response to aerosol loading in simulations in the orange that use the conventional storm resolving resolution in an MMF, and you can see a pretty big increase, 5 grams per meter squared on average increase with not much seasonal variation. And the blue dots show you what happens when you refine the resolution at great computational expense of each of the models. And it looks on the one hand like not that dissimilar a liquid response, but behind the circles, if you look at the triangles, you can see a regime dependence emerging that's quite important. Actually, the upward facing triangles separate the non-raining clouds from the raining clouds, and they have an opposite signed response. So they actually decrease their liquid in response to aerosol loading. And it makes sense that non-raining clouds don't participate in lifetime effects, and this is a feature that's observed in observations and in large eddy simulations. That it's nice to see you can make a global model produce when you add explicit boundary layer turbulence. Now, of course, there's problems with these approaches. There's biases that have been difficult to control. And one of our longstanding ones has been a dim bias in the stratocumulus zones, which is not what you intend to do when you add high resolution to an MMF. But I think a lot of these problems are just associated with not understanding how to tune multi-scale models well. And there's progress on that front. So here's an example of some work where we've just added some hyperviscosity to the cloud resolving model. On the right-hand side is what happens normally, where we have a lot of high frequency. So we're looking inside an individual cloud resolving model right now at the updrafts and the downdrafts in the colors and the cloud associated with them in the black contours. And we realized by looking at images like these that when you have more than one cloud resolving grid column resolving an individual boundary layer eddy, it's appropriate to add some hyperviscosity, because look at this grid scale noise that builds up immediately. It's a predictable consequence of the leapfrog momentum solver in the cloud resolving model that we use. And so for the same reasons that we apply scale selective hyperviscosity to GCMs to avoid grid scale pileup of noise, there's philosophical reasons to do the same thing in the cloud resolving models once you begin to not rely on grid scale eddies to provide your enthalpy transport. And various tunings like these can fix the dim biases in the stratocumulus. Here's an example showing the brightening of the clouds that happens in response to this hyperviscosity tuning. And there are other insights being drawn about how to control MMF rainfall biases in the Department of Energy's latest experiments with MMFs at coarser resolution internally and higher resolution externally. So I want to just conclude with some remarks looking ahead. I'm really excited. Of course, we would prefer not to use two-dimensional domains that have very small extent and coarse resolution. I think there's a lot of room to relax some of those unsatisfying compromises. We'd rather do things that approach real LES that are, three-dimensional and closer to 50 or sub 50 meter horizontal resolution to get increasingly explicit and credible with boundary layer turbulence and low cloud feedback. And I'd like to suggest that raw computing power isn't the main issue. There are incredible clusters proliferating nationally. This is the latest one I love at Texas Frontera, over 8,000 really high quality Intel nodes. And journalists there will tell you they're surprised by how few climate applications apply, what fraction of this machine is occupied by non-climate science research. So there's plenty of compute cycles to exploit. But the actual potential of turbulence permitting MMF has never been explored at parity with global cloud resolving models, which can run easily on 100,000 cores. The 2-degree MMF might have 14,000 embedded LES. The maximum cores I can use is 14,000, and there's inefficiencies that mean I frequently will use 1 to 6,000. So there's a big computational parity mismatch there. And we proposed a couple of years ago, and I want to acknowledge CLD funding to support this idea, to try just outsourcing the calculations to a separate executable that's able to parallelize them and do more efficient MPI handshakes with CSM to try to access this larger core pool. And I'm pleased to announce the concept seems to work. This is a result that shows on Cheyenne going to 2x and then 4x on the x-axis, the theoretical maximum core limit of an MMF with near linear scaling for doubling and close to 70% efficient scaling for quadrupling the number of cores. So I think there's computational cushion here that can already be exploited to get more resolution and dimensionality into MMFs. And if you combine that with the regionalization capability, there's a lot of room to relax our usual idealizations and keep asking questions that I think are important to ask about how our view of low cloud and turbulence mediated feedbacks changes when we avoid parameterization and try to be increasingly explicit with the sub-kilometer scale regime. So the other thing to look ahead to, that is why I'm still interested in MMFs, is the exciting promise of machine learning. Why is it exciting? Because, well, we have this trade-off with supercomputers and convection permitting resolution, and it normally assumes the job is really hard, that the mission is simulating the whole atmosphere for decades. So of course, we can't have satisfying 3D turbulence calculations, and I have to make approximations like this in an MMF. But in the machine learning era, the job could change to just making short simulations for the purpose of mining their essence, like Pierre Gentine was showing us is possible to train machine learning emulators. And if that's the case, then we can already do much more justice to turbulence physics today. So that's why there's breakthrough potential possible there. We asked in 2017 the null hypothesis about whether this is possible, and we used a super-parameterized version of CSM to find out, just on an aquaplanet, by targeting each of the scale interactions between each of 10,000 cloud-resolving models and their host model, and treating those as inputs and outputs to a dumb sheet of digital neurons, and proved that it's actually possible to fit 70%, over 70% of the variance was deterministically predictable in these important blue regions of the atmosphere and the mid-troposphere. And since then, in the last 5 years, there have been a few other important developments, all again using the MMF as a test bed because it's so convenient. It avoids all the philosophical issues of coarse grading, cloud resolving modeling simulations. You've got a natural scale separation built in. So we were able to show in 2018 that you could sometimes get away with a coupled simulation that actually worked and ran a lot faster. In 2019, the mass and energy conservation problem was solved just by redesigning the architecture. And there's no trade-off with the fit accuracy. And then lately, we've been looking at climate invariant renormalizations to shield emulators from out-of-sample extrapolation. Those papers you can read about there. But this is a really rapidly moving research frontier. And I want to point out that, there are some shiny results that have been amplified in the literature, like this one in the middle panel, that's a neural network powered version of CAM making the same equatorial wave spectrum as the SP-CAM that's much more expensive to run on the left. But more often the case, what you see are explosions like this, that the emulators they have imperfect emulation causes blow-ups with the large degrees of freedom available once coupled to a host model. And controlling these explosions is an active research frontier. So, and again, MMFs provide this perfect test bed for that. And there's lots of lessons emerging. I'm confident that there's going to be a step change in this as the LEAP STC starts to create community benchmarks based on the SP version of CSM to engage real data scientists to do things like Pierre was showing us, to use latent spaces to reduce the dimensionality, to use causal filtering to focus on the most important inputs. And there's so many ideas for how to control these instabilities that haven't been explored yet. And maintaining super-parameterization in the CSM, I think, is just vital to those efforts because you frequently have to regenerate training data if you realize the input vector has causal ingredients you haven't articulated the first time around. And regardless, you need to have a trustworthy physical benchmark to validate prognostic errors against. But if successful, if the community can iterate, I really think this could revolutionize the resolution we think is affordable today and democratize the high resolution physics we can already afford to those that don't have access to really large computing allocations. Here's a few take-home points. Hopefully I'm not too late. And thank you for your time. Thanks to CLD and for the funding. And yeah, thanks again for squeezing me in today.
All right, thank you, Mike. So we have a time for a specific question. Oh yeah, so I see Julio has raised his hand. Go ahead, Julio.
No, I don't want to take the question if there's another question from the audience.
Well, the only question is from Steve in the chat, which is you mentioned the MMF, and I think there's a little bit of a terminology difference between MMF and what's traditionally referred to as SP within the CESM framework. And I'm curious if you could talk about well, Steve's asking, is there a CESM MMF? Which I think maybe you could answer that quickly, but maybe
for sure. Yeah, so the MMF was really investigated during an NSF Science and Technology Center called CMAP, the Center for Multi-Scale Modeling of Atmospheric Processes, that went from 2004 to 2014. And as part of its legacy, super-parameterization was ported into the CSM and has been maintained as a physics option ever since. So anybody can turn on the super-parameterization switch in modern versions of the CSM, and that's part of why the community can do machine learning emulation of super-parameterization quite naturally with an open source code. Did I answer your question, Steve? Or?
Yeah, Steve, did that answer your?
Well, I guess I'm curious because the SP-CAM parameterization, while it's been maintained, hasn't been. We have not run any scientific checks on it since CESM 1.1.1. and the code hasn't changed. So I don't know what it does scientifically right now when you run it, because the model underneath it has changed quite a bit. And so I'm just wondering, how is that SPCam being validated as the model moves forward, but SPCam has not?
Yeah, that's a great question, and it's good to know it's not being internally validated. So I guess it's the distributed community that's running it that's validating it against. I can say that I've run multiple versions of it, and we have to do microphysical tunings of the sort that are done internally for CSM releases in order to get good validation against top of atmosphere and radiative constraints, etc. But the physics inside SP are self-contained just to a large extent. They can, they're not dependent on the external microphysics that are evolving in CAM6, and they largely subsume the boundary layer scheme and the microphysics scheme. So I think there's reasons to expect fewer clashes with evolution in the exterior code base, and that's been my experience too, as part of why you can vary the vertical grid without expecting major problems.
So I think maybe related to that is Peter had a question actually in the chat, which is related to what die-core are you specifically using in your experience with CSM SP, but I think probably because I think now you can see the questions are starting to get tuned towards our discussion later in after the second set, which is really focused on the survey results. But I'm curious if you could talk about what die cores you've been using with SP and how you see that as a.
Sure. Yeah, I've been using SP for so many years that I've experienced it with the old semi-Lagrangian spectral die core and with the finite volume die core and with the spectral element die core. And to my view, that the die core doesn't matter so much compared to the SP interaction. I know that there have been concerns about some grid scale speckle that's been emerged, especially with the spectral element die core. If you don't use a physics grid remapping, that can be amplified by the MMF, but the emergent phenomena don't seem to care about that as much. Yeah, I don't know if I'm speaking to your interest, Peter, but for a while I was really worried that our over-entrainment problem in the high resolution MMF came from the die core, but even large variations in the hyperviscosity of the FV die core disprove that. But yeah, it should be, since it's a physics option, it should play nice with any die core.
Yeah, I think that's partially that probably answers his question in part because he was wondering about the issues with the SE grid, but also with using the physics grid, but also the implication of if there are die cores that are going to be sunset within the development, with the continuing going forward version, doesn't mean that you can't download CESM 1 or CSM 2.1 and use them if that would be an issue for the super-parameterization. But Julio, did you want to ask a question, or do you want me to open it up for general discussion?
Well, sure. I'll just ask real quickly. You must, for many applications, still need a boundary layer scheme, right? You need a vertical diffusion scheme of some kind. What is SPCam using now? And can if you're doing these 2D lanes, can you really ever get away from needing to parameterize kind of turbulent processes somehow?
Oh, that's a great question. Yeah. So when we use coarse resolution SP, the boundary layer scheme is partly subsumed. So the vertical diffusion of scalars is bypassed, and a spike, the land model instead passes a spike of dry static energy and moisture to the actual cloud resolving model, which naturally diffuses them in part through its own subgrid scale scheme, which is like a 1.5 order TKE closure Smagorinsky style, or if you choose a club-based scheme. There are other ways to cope with the two-dimensionality problem for momentum. The explicit scalar momentum transport is a way to just pretend momentum's a scalar and diffuse it down gradient. And Stefan Tulek had a nice paper in 2015 showing that does nice things to tropical cyclone organization. And the DOE team is going that way, although I don't think that feature exists in the CSM version of SP. I personally think that just high resolution MMF is the way to go to to challenge ourselves to regionalize the high resolution to where we really care about it for small process studies, and to just bypass these assumptions by using three-dimensional domains that have enough vertical and horizontal resolution to do quasi-explicit boundary layer dynamics that aren't relying as much on their subgrid scale scheme. But I'm biased. That's my interest, and you can't do that globally. But then, did I speak to your interest, or?
Yes, no, that answered. So you're advocating going to sort of these three-dimensional cubes, maybe?
I mean, there's CSM as a grassroots community with all sorts of different interests, right? And yeah, but that's one limit that's really interesting that I think is hard to do with any other modeling framework. But you can really bypass boundary layer schemes now. For instance, if you want to study the boundary layer response to tropical deforestation and its global climate feedbacks, including ocean coupled feedbacks, and this is where having SP within a model that's got an actively developing ocean component is so vital. You can do that. But yeah, I'm not aware of another modeling framework where you can really do that as interactively with the other components of the climate system. But there are plenty of phenomena where you're not as concerned with the boundary layer schemes mixing, where you're more concerned with mesoscale storm dynamics or larger scale phenomena where where I think there's been evidence that phenomena have hung together despite the idealizations of the MMF, despite the awkwardness of having to rely partially on the GCM side boundary layer scheme for momentum, while also subsuming the GCM's boundary layer scheme for scalars. That that if you're producing the right wave spectra and the right phenomena, there's reason to be convinced that the climate sensitivities can still be studied. With a grain of salt, though, because there are idealizations there.
Thank you.
So I'm wondering if well, Mike, if you don't mind, stop sharing your screen, and then
Sure,
we have about 10 minutes left of the full discussion, and of course we can continue this discussion, but I wanted to open it up also to questions more broadly related to the talks, and some of this discussion is setting up our discussion later, which is useful as well. But this brings up well, Brian Medeiros brought up a good question in the chat, which isn't just true for the maybe MMF frameworks, but it's also true for any type of regional refinement approaches. Does anybody have thoughts of whether there's a good kind of, or should we be creating some type of guidelines for load balancing when you're setting up different domains with high resolution, whether it's MMF or whether it's actually using the VR capabilities of, for example, the spectral element dicore, of how to handle right. So one of the things here is when we start to develop a workhorse model that maybe has a lot more functionality in terms of focusing domains on your science question, which I think is partially what Mike was advocating towards there. It also means that the balance or the needs from the support team and the software engineering team might come in, because there is these big questions about potentially load balancing. And so I wonder if anybody wants to talk to that. I see, Peter, you've raised your hand. Did you want to add to that, or do you have a separate question? Because it seems that Mike provided a link to answer Brian's question. Oh, Peter, I called on you. I don't know if you can, if your hand is up, but yeah. There you go.
Can you hear me?
Yes, we can.
But this is not. This is a different question.
Yep, that's okay.
Oh, okay. So Mike, thanks for a really nice presentation. Some years ago, Steve Goldhaber and I worked with CSU on a version of SPCam where we relaxed the periodic boundary condition assumption for the SP part of CAM. I remember Steve worked weekends and nights to get that working. I'm just curious if there's still interest in that version or where that has gone.
That's great to know about. Yeah, I've wondered about this, and I'd love to talk to you offline more about it. But I guess it speaks to the fact that too much of this SP development work, including my own, has happened in silos that aren't integrated the way they should be with the main development branches of CSM.
Okay, thanks.
Yeah, I see Rich has a question.
Yeah, Mike, I mean, could you see like 2 or 3, maybe 4 configurations of SBCam that would cover the bases without killing us with essentially a separate whole model with a separate whole set of use cases kind of thing?
Yes, I think there are, and they would probably sort themselves on an axis of computational intensity. And I wonder if one should prioritize the lower intensity ones that would be more accessible to a broader community, or not kill the NCAR compute budget, even with Duretto. Yeah, but yeah, I think there's natural ways to sort by microphysical complexity, by resolution. There've been, validation of 1 to 4 kilometer physics, validation of 200 meter physics. They have different tuning demands, but these are separate tuning exercises, and none of these models have been exhaustively tuned, and it's probably beyond our capability to tune them exhaustively. And so they should come with a warning, and they should, yeah. But I think guidelines would be helpful.
Yeah, I guess I'll just add on to that from the discussion side of things. This is kind of true, right? So there's many of us in the community that use different versions of CAM5 physics, for example, and whether we're using prognostic aerosols or not. And there's, of course, we understand that there's ways to, toggle different aerosol models, for example, but once you start to do that, you start to get out of this scientifically validated version, or if you're changing resolution, like many of us do, or using variable resolution. And I think that we've talked about this in previous working group meetings. I think, setting up or considering some best practices for how to do some maybe high level tuning of kind of, let's say, non-scientifically validated versions of the model, which I think most people on this call that are using the model are actually taking them out of the official science validated versions oftentimes, to either test for development or to test for, or to use it for specific science problems. And I think that there might be a need as we start to come up with, maybe a narrower set of workhorse models that or the next versions that are supported. I think having more information on how individuals can do some high level tuning could be helpful. And I think that gets at the question that Mike just answered. So Brian, did you want to?
Yeah, I wanted to take Mike off the fire for a minute and go back to an earlier talk. There was a discussion in the chat about Club MF and what are the limitations as we go to higher and higher resolution. So this is not entirely separate from MMF and high resolution and regionalized discussions, but I'd love to hear more about what are the limits of the Club MF approach in terms of going to high resolution. And Adam seems to indicate that we're still assuming that the ensemble of convective plumes are much, much smaller in area than the grid size, which seems like a fundamental limitation for how high a resolution we can do with Club MF.
So this is Joao. Can you hear me?
Yeah.
Yeah. So there are there are the limitations of Club, but the limitations for the multiple plumes exist. But on the one hand, they can actually be nicely sort of overcome and addressed. So it is true, as Adam said, that we're still assuming that, for example, the mass flux updraft area is somehow negligible in the approximations of the equations we make. But of course, when we actually do it in the fluxes, that's not the case, right? And it's also used for radiation. So it's part of the calculations related to the radiation interaction with clouds. So it's not completely neglected. However, it is neglected in the initial approximations that you make to get to the equations you want. On the other hand, we already have shown in single column model that there's ways of addressing this and having the updraft area as part of the entire formulation. So there's a paper from 2019 from Kai Susha and others that shows that. So this is what we would like and want to implement in practice. This is not what we have right now because we have had to sort of establish priorities. So there's a lot of stuff we haven't done yet, but our priority has been in the last 6 months to actually be able to show that you can produce a climate that is realistic compared to control versions without ever calling an explicit deep convection formulation. Now we're going to add a lot of these extra complexities. One of the things that is really nice about the multiple plumes is that it allows us to address this sort of stochastic issue, right? I mean, the fact that as you go to higher and higher resolutions, of course, each grid box is going to cover less and less plumes would exist in a particular grid box. But because the modeling itself is stochastic, it allows, with some additions, it would allow you to have a formulation that would basically, if the resolution is very high, would call the multiple plume routine, and would, depending on the size of the plumes versus the size of the resolution or the grid box, would allow you to stochastically sort of randomly sample a distribution of potential plumes, and in that sense, you may or may not have convection in that particular grid box. So that sort of formulations we've tested as well in single column model, and we haven't implemented any of that. But from a theoretical perspective, that's actually fairly plausible and defendable. So we hope to do that, and we plan to do that when it gets to that. But we still need to add other things as well, as I mentioned. So I hope it wasn't too long of an answer, but the answer is yes, we can adapt to higher resolutions. And actually, multiple plumes are a naturally adaptable approach to the problem.
Thanks. That answers, yeah, that's a great response to my poorly phrased question.
So we don't have much of a break, so I'm going to cut off the discussion. Sorry, Adam. I saw you maybe came on to add something, but maybe what I'd like to just suggest that as we go into the discussion after the next series of talks, so after that, we have a 10-minute break until 12:30 Eastern, 10:30 Mountain Time. And we'll come back and we'll hear a little bit more about some of the science applications of the atmospheric model. But we can come back to some of these discussions, particularly related to the development and future development of CAM in our open discussion later on. As well as maybe have a discussion about, right, we've seen some promising advances, and I think it'd be nice to have a discussion about, how do some of these advances make their way into whether it's CAM 7 or maybe CAM 7.x. I think that's a good discussion to have in our fuller breakout later. So with that, I will see everybody back here in 9 minutes, and we'll turn it over to Christian to chair it at that point. So see you all.
Yeah, welcome back to the second half of the AMWG session. Alyssa, are you already on? I don't see you.
Yes, I'm here.
Good, perfect. Yeah, I think we should get started. Again, we have about 15 minutes, and this should include a question or two if you allow it. I will turn on my camera maybe at the 14-minute mark, so you know it's, you should wrap up.
Okay, great. You can see my screen.
Our next speaker is Alyssa Stanfield, and in collaboration with Kevin Reed, and she talks about the tropical cyclone precipitation and SST interactions.
Great. All right. Thank you so much. Yeah, so today I'll be presenting on some work I've done alongside my advisor, Kevin, as kind of the last part of my PhD dissertation, which I just finished up this past May. So first, when you're thinking about the relationship between extreme precipitation and temperature, you can kind of think about it on like two different time scales. So there's like the short kind of like weather time scale, where the relationship can depend on storm type, season, localized convective feedbacks. A lot of work has been done on this relationship before. And so many studies have actually found kind of localized subdaily increases in precipitation above the 7% per Kelvin baseline kind of expectation based on the Clausius-Clapeyron relationship. And so this has been observed in certain locations. For example, if you look at the figure on the right, which is from this recent kind of summary paper, Neale et al. 2022, it shows in this green line from Lendrick et al. 2017, this like not above 90th percentile precipitation. I think this was from a location in the Netherlands or something. The rate of increase of precip with temperature change is well above the 7% per Kelvin baseline, which is shown as that dotted like black line. And then there's also, besides this short-term relationship, which is also called the apparent scaling of precipitation and temperature, then you can also think on like the longer term climate scale. So this is also called the climate scaling. So on the long term, as the atmosphere and the sea surface temperatures are warming, how is precipitation responding to that? And these two scalings are not necessarily the same. So then there's a whole nother aspect we bring in here. So looking at tropical cyclone extreme precipitation. And so one problem in looking at observations is that in the past, over tropical oceans, observations have been kind of spatially sparse and not very frequent. So therefore, it's tough to estimate the apparent scaling. And then we also only have 20 years at most of more high resolution observations. So therefore, it's also tough to estimate climate scaling from this kind of short time frame. And the climate scaling is probably what I'd say, the most interest has been in understanding how TC precip will respond to climate warming. So most studies just kind of compare a historical and a future GCM simulation. So this recent summary assessment of many of these type of studies found that near storm precipitation will likely increase about 14% per 2 Kelvin of warming. So that's approximately in line with the Clausius-Clapeyron relation. And so what I've been working on is trying to understand if these idealized CAM simulations that we have, what can these simulations tell us about the response of real world tropical cyclones to climate change? So I have, again, these idealized simulations, which I'll explain in the next slide, try to compare them to more like realistic AMIP type simulations, and then finally to observations as well. So these idealized simulations are, again, CAM5 simulations. They were run with the official radiative convective equilibrium model intercomparison project, CompSet, which was detailed in Kevin and co-author's paper from late last year. And so we use the protocols of this RCE MIP, except one change is we add rotation. So the model is rotating at the same rate as the real Earth. So we have 11 simulations with globally uniform SST varying between 295 and 305 Kelvin in 1 Kelvin increments. The horizontal grid spacing is about 28 kilometers. We use the SE dynamical core. And so since these are RCE simulations, there's no seasonal or diurnal cycles. And if you want more information about these simulations or the TCs in these simulations, we I published this paper back in 2021 about these simulations. So then for more like the realistic model simulations, we also use some CAM5 simulations. They're AMIP simulations for 1980 to 2012. They have the same horizontal grid spacing of about 28 kilometers, also the SE dynamical core. And so these simulations were also used to study TCs in these couple of previous papers. So they have been used to study TCs before. And I'll just mention that to track these TCs and extract their precipitation, we use the Tempest Extreme software. So finally, observations. So I'll just mention that the time period for these observations that we have is only 2001 to 2020. So it is slightly different than the CAM5 simulation time period. We use the IB tracks data set for TC tracks and intensities. For precipitation, we're using the eMERGE satellite product. We convert it from half-hourly precip to 6-hourly to match the model output. It is at a 0.1 degree spatial resolution, but we regrid it onto this kind of common grid with the two model data sets kind of to make everything more consistent. And then the SSTs for observations are from this NOAA optimum interpolation data set. And I'll just mention quickly, so we only look at TCs that are between 5 and 20 degrees latitude in both hemispheres, just because we wanted to try to focus on the region where the idealized simulation TCs would most likely to be, are most likely to be comparable to real world tropical cyclones. And so to get into a couple of results, so looking at TC intensity, we have the RCE simulations, the idealized simulations are black, observations are blue, CAM5 AMIP simulations are this purple color. And so we see that actually the intensity distributions for the models are pretty comparable to observations, not too far off. The medians are shown on the x-axis in the diamonds. And so for both measures of TC intensity, the maximum wind speed and the minimum sea level pressure, the models underestimate the intensities a little bit, but overall really not too bad. Next, we look at TC precipitation radial profiles. And so on the x-axis here just shows the distance from the TC center, and the y-axis is showing the precipitation rate in millimeters per day for RCE CAM5 observations. And so we see when we're looking at the values of the precipitation in these radial profiles, they're actually pretty comparable between all the data sets. CAM5 is actually higher than observations in some cases. Sorry, I forgot to mention, these are split up by sea surface temperature, going from 299 Kelvin to 303 Kelvin. And so again, we see the values between the data sets are actually fairly similar. However, the response of the profiles to SST increases does vary a bit. So for the RCE simulations, we see that most of the increase with SST is in the inner core of the storm. For the CAM5 simulations in the middle, there's an increase in the inner core and actually not so much in kind of the middle region and a little more in the outer region of the storm. And then for observations, there's a little bit more of like a blanket increase over most of the radii as the SST increases. So next, I kind of tried to recreate that plot I showed in the second slide. So looking at the relationship between SST on the x-axis and precip on the y-axis. So here I'm showing, I take each TC at each time step and I calculate its 99th percentile precipitation. So an extreme precipitation metric. And then I bin the storms based on the SST that is underneath them. And so the color scheme is consistent here. Blue is observations, black is RCE, purple is CAM5. And so in the background, those kind of faint lines, the gray dashed line shows the Clausius-Clapeyron rate of about a 7% increase in precip per degree Kelvin increase in SST. And then the faint red line is a double Clausius-Clapeyron rate. And so we see that for especially observations and CAM5, they both seem to increase at kind of above the gray line, just the Clausius-Clapeyron rate, probably more in line with this double Clausius-Clapeyron rate. And then the RCE, it's a little harder to tell because again, we only have the RCE at 299 Kelvin, 300 Kelvin, 301 Kelvin, and so on. But it's kind of seems to be a little bit more between the gray and the red line. So there seems to be a little bit of less sensitivity of 99th percentile precip to SST in the RCE simulations. So next, and I'll just go over this fairly quickly, we tried to break down the precipitation increase with Kelvin into kind of thermodynamic and dynamic components. And so more information about this equation is found in that paper that I'll mention again on the last slide. And so basically we just use kind of this partial differentiation breakdown and some regressions to try to estimate how much of the change in TC precipitation is due to, one, the change in moisture available versus the change in TC intensity. And so this is kind of just the same thing. And so what we found was that looking in the black column is the total kind of change in 99th percentile TC precipitation per Kelvin. So again, we see consistent with the figure I showed 2 slides ago, the RCE only shows a 6.1% increase per Kelvin, whereas CAM5 and observations are a bit higher, with observations being the highest at about 15%. And so for all of them, the thermodynamic contribution dominates over this intensity contribution. So for CAM5 and observations, the intensity contribution is actually around 0. And this is mostly due to this last term shown in this equation, this dV dSST term, because we found that that relationship was like very small, even slightly negative in how we were calculating it. So that kind of made the intensity contribution fairly small, but it's higher in the RCE simulations. So just quickly, I'll go over some results. So again, for this kind of apparent short duration scaling, it seems that TC precipitation is a bit less sensitive to SST in the models than in the observations, but this is especially apparent for the RCE simulations. For all of the data sets, we found that the majority of precip change comes from the thermodynamic contribution. And again, in CAM5 and observations, because the TC intensity change with SST is like very small, that leads to the very small contributions from intensity change. And so we're still working on trying to explore how we could possibly use these RCE simulations to try to understand the climate scaling between TC precipitation and SST and try and relate it to observations. This is still a work in progress. I was literally like messaging with Kevin this morning about this work, so still working on it. But ultimately, I'm trying to see if we could try to use these RCE simulations to like project future TC precipitation increases as we continue to see sea surface temperatures warming with climate change. So that's all I had for today. Again, this is this paper that came out about the RCE simulations. If you're interested, I hope to publish or submit a paper about this work that I presented today very soon. I'm happy to take questions now or in the chat or through email. Thank you.
Thanks a lot, Alyssa. We have a chat question. So Jiangning, if you want, you can just speak up and ask your question.
You're really, really low. I could kind of hear
better?
you.
Is that better?
Yeah. Yes,
okay.
I can hear you.
Cool talk, thanks. Just wondering about the table that you showed. I think for RCE, the thermodynamic, sorry, it's the other way around. So for CAM5, the thermal contribution is like almost 100%, but for RCE and OFS, it's a little lower. What are some of the thoughts for the OFS part of like where that precip increase is coming from, like aside from the thermodynamic contribution? Because that I'm asking because that might relate to like how people want to interpret the idealized simulations. So just wondering what your thoughts might be.
Yeah, no, that's a really good question. I think I'm still trying to understand this exactly. I think there probably is, like, at least on the climate scale, there's probably more of an increase from intensity that is not showing up in these results because of how I calculated this dV dSST term. So I think probably in the long term there would be a contribution from intensity. I guess there probably could also be some sort of maybe some microphysical changes that are showing up in the observations that maybe wouldn't in the models as well. So that's one thought. Yeah, maybe like precipitation efficiency changes, perhaps. Just a guess, but yeah, I think I need to think about this a little more. It's a good question.
Yeah, cool. That's definitely a difficult one. Thanks.
Yeah. So I see Rich has raised his hand, but Rich, I think we should actually stick with the schedule. Sorry, can you table your question for the discussion period, or even ask it in the chat, please? Thank you. Okay, we stick with the tropical cyclone topic and also high resolution. Our next speaker is Pavan Ravi. And she will talk about ultra high resolution modeling and tropical cyclones. Take it away.
Yeah, can you see my presentation?
No, we see the other screen. I think your presentation just moved. Yeah, it's coming. Can you do full screen?
Yes. Can you see the full screen?
No? We still see your, no, I think your full screen is not visible to us.
Okay.
Maybe you swap displays.
Or share your entire screen.
Or share your entire screen, yeah, thanks for. I guess that's the same issue we had before.
If you press that play button, it'll go to full screen presentation mode.
Yes.
Yes.
Great.
Thank you. Yes. Yeah. Hi everyone. I'm Harika. Currently working as a postdoc at IBS Center for Climate Physics, South Korea. Today I'm going to present on orbital and CO2 effects on tropical cyclones using ultra high resolution CESM model. And yes, before going to that, I would like to show the recent IPCC report about tropical cyclones in future warmer climate. And there is indication that there are more major tropical cyclones and as well as more better and windier tropical storms. And also they're moving, shifting towards north, as well as they're rapidly intensifying tropical cyclones due to increased sea surface temperatures, as well as there is also indication of the slower TCs, which can do more damage. And coming to the TCs and climate, in the warmer climate, there is a consensus of increase in tropical cyclone intensity between models and as well as the tropical theory. But coming to the frequency, there is an uncertainty because some of the studies project an increase and there are some studies project a decrease in the tropical cyclone frequency in the warmer climate. Therefore, understanding the large-scale climate controls and tropical cyclone frequency using the high-resolution models is useful for better risk assessment as well. Yeah, so my objectives are to look at how different are the orbital forcing and greenhouse gas forcing derived large-scale climates, and what is the effect of these varied large-scale climates on frequency and intensity of tropical cyclones, and also to look at if there is a common relationship between large-scale climate conditions as well as changes in tropical cyclone characteristics in the past and the future climate. Coming to the past climate, I have considered two simulations which are due to changes in the precision index. Like one is the MIS 5E, where there is the low precision index. That means that there is high solar insolation in the northern hemisphere summer. And in MIS 5D, which has high precision index, that means there is high solar insolation in the southern hemisphere. And these changes in the solar insolation may lead to changes in the large-scale climate variables. And the future climate, I'm looking at the simulation of 2 times CO2, doubling of CO2 conditions. And yeah, I will discuss these results in the next slides. And for this, I'm using CESM 1.2.2 model with atmosphere 25 kilometers and ocean 10 kilometers. As I explained earlier, there are two past simulations which are looking at the role of orbital forcing because the other conditions are almost similar, except the change in the precision index. And to look at the effect of greenhouse gas forcing, I'm looking at 2 times CO2 and comparing with the present day climate. And yes. And for this, I'm using 2 different types of tracking schemes. One is the traditional tracking schemes, like which uses resolution dependent thresholds to detect tropical cyclone-like vortices. Like those thresholds are the surface pressure, absolute vorticity, 10-meter wind speeds, and duration thresholds. And the second one is the phenomenon-based tracking scheme, which usually detects the locations potential for cyclone formations. They use the resolution independent thresholds, like those are Abukovice's parameter, relative humidity, vertical wind shear, specific humidity, and the duration thresholds. And yeah, this slide shows the changes in the large scale variables. Like the left side shows the first is the precision index and the CO2 levels and the tropical SSTs. These are simulated using low resolution CESM model. And you can see the variations of the CO2 levels match with the tropical SSTs. And the past warmer climate, like the past conditions like MIS 5E can be an analog for the future warmer climate, looking at the values of CO2 and the tropical SSTs. And here in this panel, it shows that the dotted line shows the tropical SSTs using the proxy data. And the proxy data matches well with the tropical SSTs of the CESM model. And yeah, I wanted to look whether the past warmer climate like MIS 5E may be an analog for the future warmer climates like 2 times CO2 or not. Like the right side panel shows the variations in like solar insolation, temperature, specific humidity, and relative humidity, and like annual changes. We can see that there is variation between orbital and CO2 forcing because there is difference in the solar insolation and the orbital forcing in northern hemisphere and southern hemisphere. So we see an asymmetry in northern hemisphere summer and southern hemisphere summer seasons of like the temperature, specific humidity, and relative humidity. And these changes may lead to the changes in the tropical cyclone genesis or intensity variations. Like to look at that, I used Genesis Potential Index, like to look at the tropical cyclone genesis. And the left panel shows the compares between 2 orbital forcing simulations. And the other panel shows the 2 times CO2 and the present compared with the present day climate. And here we can see that in the orbital forcing simulations, there is an asymmetry in the northern hemisphere and the southern hemispheres. Like there is an increase in the southern hemisphere tropical cyclones in the orbital forcing simulations, but in northern hemisphere we see an asymmetry, like a decrease in western North Pacific and the North Atlantic, but increase in the North Indian and Eastern North Pacific. And whereas in 2 times CO2 conditions, we see a overall decrease in the frequency of storms in across the globe. And these differences in the genesis potential can be explained by use of using the component analysis, the GPI component analysis, to see which variable is able to explain the changes in the genesis potential index. And of all the variables, I can see that the moisture entropy deficit variable is explaining the changes of genesis in both the orbital forcing simulations as well as and in the future warmer 2 times CO2 simulations. And I used another genesis potential index as well, which uses different variables. Like here, instead of moisture entropy deficit, the additional variables are the relative humidity and the vertical velocity. And these genesis potential changes also indicate that here also the 700 hectopascal relative humidity explains the changes in the genesis, tropical cyclone genesis changes. And this slide shows the tropical cyclone genesis and tracks, which are explicitly simulated using the tropical cyclone tracking scheme, which I have explained earlier. And here we can see that in the MIS 5E, there is higher annual frequency compared to the present day. And on 2 times CO2, we observe a decrease in the frequency of formations compared to the present day. Although, and here the annual frequencies in the northern hemisphere and southern hemisphere shows differences in the orbital forcing simulations. Like in MIS 5E, we have higher frequency in the southern hemisphere basin compared to the in MIS 5D, whereas in northern hemisphere we see that MIS 5E has higher frequency in northern hemisphere as well, whereas in 2 times CO2 we observe a decrease in frequency in southern, more decrease in the southern hemisphere compared to the present day. And looking at the tropical cyclone genesis density differences, which are measured within a 5 degree by 5 degree box region, we can see that there is an asymmetry in the orbital forcing simulations, like increase in the southern hemisphere basis, and a symmetry in the northern hemisphere, like a decrease in the western North Pacific and in North Atlantic basins, and increase in the North Indian and Eastern North Pacific. And in 2 times CO2, we see an overall decrease in the across all the ocean basins. This genesis density differences are using the explicitly simulated detected tropical cyclones. And while looking at the annual frequency, annual cycle of the tropical cyclone frequency, almost like the model captures reasonably well like annual cycle in most of the ocean basins, except the western North Pacific. And there is an underestimation of tropical cyclone frequency in the North Atlantic basin as well. And as a test case, I have looked at one of the model is able to capture the category 4 storms in 2 times CO2 and also in the MIS 5E and MIS 5D simulations, like orbital forcing simulations. And this is one of the test case where we can clearly see the tropical cyclone I and the sea surface cooling, which is captured using this model. And looking at the tropical cyclone intensity changes, globally we see an increase in the frequency of intense storms in 2 times CO2 simulations. When coming to the orbital forcing simulations, we see a symmetry in the northern hemisphere and southern hemisphere. In northern hemisphere, we see a decrease in the frequency of intense storms in MIS 5E, whereas in southern hemisphere, we see an increase in the frequency of intense storms in MIS 5E simulations compared to the MIS 5D. And these changes, like we can see the changes in the tropospheric temperature and moisture conditions. Like here we can see an asymmetry in the orbital forcing simulations of temperature, humidity, and relative humidity. And in 2 times CO2, we see overall similar changes in across the northern hemisphere and southern hemisphere summer seasons. And here we can see that relative humidity changes explain the changes in the tropical cyclone frequency. Like in the southern hemisphere summer season, there is higher relative humidity, which is leading to favorable for tropical cyclone formations. And in the northern hemisphere summer season, there is a decrease in the relative humidity in the orbital forcing simulations, which is leading to the decrease in the tropical cyclone frequency. And looking at the 2 times CO2 conditions, we see that globally there is a decrease in the relative humidity, which is leading to a decrease in the frequency of formations. And also I have looked at the static stability of the atmosphere, and we also see this in MIS 5E. So northern hemisphere has higher stable conditions compared to the MIS 5D, which is also leading to the reduced frequency in northern hemisphere seasons. And in southern hemisphere, we see MIS 5D has higher stability and stable conditions than MIS 5E. Therefore, we have higher frequency in MIS 5E compared to the MIS 5D simulations. Overall, we see an asymmetry of tropical cyclone formation and intensity in the orbital forcing, whereas symmetric changes are observed in CO2 forcing. And Northern Hemisphere summer in MIS 5E cannot be an analog for CO2 forcing conditions, because we find an asymmetry in the formations in Northern Hemisphere basins, like increased frequencies in North Indian and Eastern North Pacific, but decreased frequencies in Western North Pacific and North Atlantic. Whereas overall in CO2 forcing simulations, we see overall decrease in Northern Hemisphere basins. Also, we can see that moisture-related variables explain the changes in the tropical cyclone frequency in past and future warmer climates. And coming to the intensity is mostly based on the tropospheric changes in the temperature and moisture conditions. Yes, thank you.
Thank you. We are out of time, so in case you have questions, I would like everybody to push them into the discussion section. And let's move on with our next speaker. And please stop sharing the screen.
Yes.
So, Pavan, we still see your screen. If you could
yes, one second.
Stop the screen share. And then we move to our next speaker, and it's Wilku Karol. And we are sticking with this theme of high resolution. In this case, it's variable resolution. Take it away, Wilku. If you move to the full screen mode, and you're also muted.
Can you see my presentation?
Could you move into a full screen mode?
Yes, okay.
Yeah.
Is it okay now?
Perfect. Yeah, take it away.
Sorry. You can't hear me? You can?
Yes.
Okay. My talk will be about an application of community atmosphere models, spectral element dynamical core option. This option gives us ability to study variable resolution within a global context. It gives us opportunity to overcome some pitfalls of regional climate models and make simulations cheaper than global high resolution models, yet obtain comparable results over our domain of interest. Sorry. For our study, we generated a variable resolution grid using open source software package SquareGen. Our grid has a base resolution of 1 degree all over the globe, but over our domain of interest, it is refined to a quarter degree high resolution. Between the high resolution region and the base resolution, there is a region of transition which has a resolution of half degree. When we want to compare the cost of variable resolution grids, we can assume linear scalability between the number of elements within the grid and job walk clock time. So we can say that our variable resolution grid has less than 2 times cost of uniform 1 degree spectral element grid, but it's likely to give us comparable results of uniform quarter degree high resolution grid over our domain of interest. For our study, we completed 2 sets of simulations. One set consists of control simulations, which has a uniform 1 degree resolution. And the other set consists of variable resolution simulations with a highest resolution of a quarter degree. We made our simulations using FIS ComSet for between 1998 and 2015, and both control and variable resolution simulations consist of 7 ensemble members. Today I will only present you near surface temperature and precipitation results, but we made some analysis with other variables, including upper layer atmosphere variables. But these are our first results. The plots are for annual global temperature. As you can see at the two bias plots below, our variable resolution model gives us comparable results with control simulation, but better biases over, especially over high elevation terrain. When we look at our region of interest, our variable resolution model performs much more better than the uniform 1 degree control simulation. We applied a bias index both for temperature and precipitation. The red regions shows us the regions where our model, our variable resolution model performed better than 1 degree uniform control simulation. And as it is seen in the plots, red regions dominate the blue ones. These are for annual total precipitation. Again, we obtain globally we obtain comparable results with uniform 1 degree control simulation. But when we look at our region, we can see that our model performed better than the control simulation. Again, especially over complex terrain. We applied this index to precipitation also. Although it needs further analysis, over the regions where correlation is significant, the results are again comparable for precipitation. So I want to present you our preliminary results. Variable resolution CSM produced either better or at least comparable statistical biases to be uniform 1 degree control simulation. It better represents regional dynamic processes modulated by complex topography. The temperature biases over our domain are noticeably smaller for VRCSM. There are high spatial correlations with RFI-free analysis data set. So our region is a great testbed for variable resolution CSM studies, and we expect to obtain good results with cheaper costs. Thank you.
Thanks a lot, Baku. That leaves time for questions. Feel free to raise your hand or use the chat. I just had a quick question, and maybe that I didn't catch it quite right. Is this the configuration with Cam 6 physics or Cam 5 physics?
6.
Cam 6, okay. So
yes.
The newest. Good. Again, if you have a question, please feel free to raise your hand. Yeah, Brian.
I was just wondering, maybe I missed the motivation, but I was wondering what your ultimate application for this configuration is. Is it climate change or is it more weather oriented?
For climate dynamics, not weather oriented, climate change, for climate change.
Thank you.
Mm-hmm.
Have you considered also comparing against observations? Which
yes, of course. These are very early, very preliminary results. We are planning to make comparisons with observation data sets to study on many variables to evaluate its added value. Because of time restriction and because our results are quite fresh, and these are just for 2 variables. But we are planning to study many variables and make many comparisons with other observation data sets.
And where do you envision this research in the future? What's really your science pursuit here?
Sorry, I couldn't understand.
Oh, where do you want to go in the future with that approach of the variable resolution? What's kind of really the science approach that you want to follow in the future?
Sorry,
I'm guessing this is related to Brian's question. Kind of, you have a scientific question probably that you are asking.
Yes, we expect an added value. Our scientific question is that with a very less cost, can we obtain a better representation of regional climate dynamics? We want to investigate it.
Mm-hmm. Yeah, Julio.
Thank you, Burcu. Do you have ideas or suggestions about orographic drag schemes at these high resolutions? You mean, I mean mountain wave drag parameterizations, things like turbulent form drag. So, the ECMWF version is Belliar's.
Indeed, I must say that I am very new at climate modeling. So I can't answer your question for now.
Do you know if your runs do have these? Do you know if your runs included an orographic drag scheme? Gravity wave. Okay, all right.
Mm-hmm.
Adam.
I guess I don't have as much of a question, but I wanted to bring forth an issue that it sounds like Mike Pritchard and people who are running SP all have an issue, is that when we generate a variable resolution grid, we do need to retune the clouds. And a lot of that has to do with we want to use a really small physics time step in variable resolution so that we don't truncate our scales in the refined region, but that ends up really screwing up our cloud fields. And so I just want to, make it clear to the group that this idea of coming up with some guide for tuning would be useful beyond just what Mike Pritchard was suggesting. And I think we do need to make steps in that direction.
Thanks, Adam. And I actually also would like to point out that Hui Wan from DOE, the PNNL lab, she also looks a lot at the time step sensitivity in E3SM in this case, but it turns out, that a lot of the physics parameterizations are very sensitive to time step settings, and it's often really grounded in the numerics of these physical parameterizations and how they are coupled to the DICOR. So it's a very important topic, Adam. I agree on that, which we should tackle for CSM as well.
Right, yeah, so the implication is that, ideally we can improve our time step convergence errors so that we wouldn't have to tune as much. But until then, we are going, so some combination of those two solutions, hopefully we can leverage in the future.
Yeah. If there are no more questions for Burcu, then let's move on. And our next speaker is Jim Morrell from Colorado State University. And he also talks about high resolution, in this case, earthworks. Take it away, Jim.
Thank you very much. This all look okay?
Yeah, it's
all right. Great. Thank you. It's good to see so many friends and colleagues really enjoyed the previous presentations. And I'd like to begin by thanking the organizers of this working group meeting for the opportunity to give an update on this project that we call Earthworks. We've tried to give an update on this project at every single working group meeting since this project began just a little less than 2 years ago. because the engagement of the CSM community into this project is something we very much welcome and look forward to. And we think it's important because I very much agree with Mike Pritchard's earlier comments that a diversity of modeling approaches is really healthy for the CSM ecosystem. And this project, Earthworks, presents many opportunities for information sharing and collaboration for all of us that are interested in high resolution modeling and its applications. I also wish to emphasize that while Earthworks is not formally a CESM project, it is based on CESM. And we are working very hard in this project to ensure that our code base remains compatible with the evolving CESM code base so that ultimately Earthworks could become an option for high resolution coupled modeling within the CESM suite of modeling capabilities. As a result, on this title slide, you'll see that Earthworks, which is being led by Dave Randall at Colorado State, has a very strong list of NCAR and CESM co-PIs and collaborators. And also, we've really benefited from contributions from the ESMF and the CSEG teams as well. So in terms of how Julio started in terms of the UCAR Code of Conduct, this is very much a team effort, and I'd like to acknowledge all of these team members. In this very short talk, I don't have time to really articulate the reasons why we might want to consider high resolution global climate modeling. I think many people in this working group are very familiar with that, as well as the challenges around it. This is just one paper that I was fortunate enough to contribute to. This was a briefing paper prepared in advance of COP26. In addition to all of the interesting scientific opportunities high resolution modeling presents, we make the case in this paper that high resolution Earth system models can potentially revolutionize the quality of information available for mitigation and adaptation decisions in the face of climate change on both global and regional scales, since the extreme weather events that cause the greatest damage are generated by processes operating at small scales, while crucially, they're shaped by the much larger global circulation of the ocean and the atmosphere. And of course, there's feedback between the two. So it's really a continuum of scales. So just briefly, Earthworks is a 5-year project funded by the NSF Directorate for Computer and Information Science and Engineering. The objective is to develop a global storm resolving coupled model capability that uses a single uniform global grid. Earthworks consists of CAM6 with the impasse non-hydrostatic dynamical core, the impasse ocean model that has been developed at Los Alamos National Labs, the impasse sea ice model, as well as the community land model and CMEPS. The goal, the ultimate goal, as I said, is to develop a modeling framework that can be utilized by the broader research community and applied across a range of leadership class supercomputers across the US. Ultimately, where we're headed, we're not there yet. We're not even 2 years into the project, but indeed is a kilometer scale fully coupled modeling capability. A lot of the effort is really moving toward utilizing GPU enabled components with end-to-end workflow portability across US leadership computing systems. And I'll say a bit more of that in this talk. A few initial objectives I just want to highlight and call out in today's presentation. One of the first tasks was porting the impasse ocean model and the sea ice models into the CSM framework, and we have done that successfully. Initially, while we're moving toward GPU-enabled components, we wanted to assemble a CPU version of this Earthworks configuration and test it out at relatively coarse grid resolutions, and we've achieved both of these goals. We're also beginning to test CAM6 physics at convection permitting scales. And I think importantly and of interest to this group perhaps is that we've been working very hard to port critical path portions of Earthworks to GPUs, and we've made good progress on that. And let me just quickly highlight some of these. So as I mentioned, the first task, assemble this version of the model, get it to run, do it based on a CPU version and see what the simulations look like, and can we produce stable climate simulations at relatively coarse resolutions. We have diagnostics for a number of simulations, including a 10-year simulation that was recently completed at 60 kilometers. It's available from the Earthworks website, which is indicated here. And this is not a talk to talk about the fidelity of the simulation at this point, but I just wanted to put up a couple of plots to show you that we are simulating planet Earth. This is surface air temperature, an estimate of the observations on the left, and from the 10-year annual mean surface air temperature from Earthworks on the right. There are biases. I don't mean to say there's not biases, some relatively large biases at this stage you can see with your naked eye. For instance, a cold bias over the Arctic region. If you look off the west coast of the continents, as is typical for coupled models, Earthworks is also simulating near surface air temperatures and sea surface temperatures that are too warm to climatology. We're not only focused on mean state when we're looking at the diagnostics, but also the variability. 10 years is kind of short to say much about INSO variability, but here we just made a plot of the North Atlantic oscillation based on monthly anomalies of sea level pressure over the North Atlantic, pretty good reproduction of this dominant mode of climate variability. And precipitation, people always like to see plots of precipitation. An estimate from observations on the left from the 10-year Earthworks simulation, again, annual mean on the right. You can see that there are aspects of the Earthworks simulation that match up with observations pretty well, but again, there's biases, pretty diffuse ITCZ over the Atlantic, too much rainfall over the Western Equatorial Indian Ocean region, and something in the Central Pacific that's quite reminiscent of the longstanding double ITCZ bias. Very recently, in fact, just yesterday, we got some plots from a new 30-kilometer coupled simulation that is running as we speak. So this is just the January from year one, nothing more than that, at 30-kilometer resolution, the total precipitation rate. So I can't really compare or say anything scientifically valid at this point, but I do think it's interesting. For instance, if you look over the Atlantic, you see a much better defined ITCZ over the Atlantic. Again, I'm not saying that's a robust feature, but this simulation is just now in the machine. When we're making these diagnostic plots that are available on the webpage, we are using a number of existing diagnostic packages, such as the Climate Variability Diagnostics Package and DOE's MPAS analysis package. But ultimately, using MPAS, we need to do the diagnostics directly on the unstructured mesh data. So we're working with Project Region. We're also working with Brian Medeiros and others on the atmospheric diagnostics framework. Region, which is highlighted here, is a NSF EarthCube project whose goal it is to develop community-owned, extensible, scalable tools for supporting analysis and visualization directly on unstructured model grids, such as those from MPAS. So very much looking forward to working with the Region and ADF teams as we move forward. Just a quick slide about the testing of CAM6 physics in MPAS at convection permitting scales. This is the simulation. Some of the details are in the top part of the slide, so I won't repeat them here. This is for one particular time period on the 26th of April, 2017, looking at observed reflectivity on the left, and then a standalone MPAS simulation with WRF physics to its right. What you see in the observations is a classic squall line structure within a larger scale structure, a comma-shaped larger scale structure. You see a very clear leading line of very strong convection and a trailing stratiform structure with weak echo region between the two. Now, when you look at the MPAS simulation based on WRF physics, overall the forecast is very good. Many aspects of the observations are reproduced, although you will note that at 3 kilometers, the model is overdoing the reflectivity. This is typical of all models at 3 kilometer resolution, and there's no significant weak echo region. When we look at the simulations with MPAS with CAM6 physics, again, we see the overall structure, but there are larger differences than we see in observations. compared to observations, with convection being forced primarily by the strong cold front, while, for example, in the war physics simulation, the convection is triggered in a warm sector ahead of the front, more as was observed. So there's some takeaways from this. The key thing I want to emphasize today is we are doing this testing. We have a lot more to do in this area, but CAM6 physics is stable at 3 kilometers, at least for this test case. I want to wrap up the talk by saying just a few words about our computational objectives. I think very importantly to emphasize to this group is that Earthworks is pushing end-to-end workflow portability across leadership computing systems, because it's important to enable this kind of climate simulation for researchers across the nation, and for researchers to be successful when they write large-scale computational research proposals in order to utilize these machines. There's really 2 keys to this aspect. The first is the portability of the environment, where in Earthworks we are experimenting with software containers like Docker and Singularity, and also performance portability, where we've taken a GPU offload via directives approach using primarily OpenACC and OpenMP, and also beginning to experiment with MPI, if you're familiar with those acronyms. It's also important to demonstrate scalable end-to-end workflows, which includes, of course, scalable I/O, which is really critically important for high-resolution modeling, efficient analysis, because we're talking about hundreds of terabytes of data here on unstructured grids. I already mentioned how we're working with Project Region, high-speed point-to-point data transfers, for example, via Globus, and data portals, which means data sharing via easily deployable containerized science gateways. Related to this, our goal is to build and test across multiple platforms and centers to ensure that Earthworks is easy to build and run. We're initially focused on a subset of large computing platforms on NSF and DOE systems. At NSF, with NSF systems, this of course includes NCAR. We have a large allocation on Cheyenne that we're utilizing. And then also at TAC, where impasse atmosphere will serve as a characteristic science application for NSF's next generation leadership class computing facility system, which is tentatively being called Horizon. On DOE systems, we received allocations to do work at Argonne, which we're using primarily for GPU porting and testing, and at NERSC, where we're doing both CPU and GPU testing. Finally, in terms of the testing status, first on CPUs, the initial goal of Earthworks has been to assemble a working CPU version, as I've highlighted earlier in the talk. This plot shows our progress in achieving this goal. The x-axis is the level of test integration from unit tests in gray to increasing levels of component integration within CESM, which are the shades of blue. And the y-axis is the resolution. And you can see that our approach here is to increase the resolution incrementally by a factor of 2. The key point is that we're trying to work up toward the upper right corner of this diagram. And overall, you can see that we're making good progress. And we've completed now a couple of fully coupled runs on CPUs at 120 and 60 kilometers. And again, a 30-kilometer simulation is in the machine right now. In terms of GPU testing, this chart breaks down Earthworks by components that need to be refactored, namely the atmosphere, the ocean, and the sea ice components. Note, at this point, we're not touching the land surface and the CMEPS mediator, which we envision staying on CPUs. In this table, the green shows those parts that have been ported and optimized to GPUs, noting that we've only looked at NVIDIA GPUs to date. But the main point is that some of the most critical path portions of the model have been ported to GPUs. We're working on Club right now, and when this is ported, we will also be able to have the CAM6 physics package operating on GPUs. Wrapping up here, just want to call out a couple of other relevant talks, including the one after this one by Xing Ying, who is a collaborator with us on Earthworks. This talk is related to further testing of CAM6 physics at 3-kilometer grids using variable mesh resolutions. and then a couple of talks of interest in the software engineering group tomorrow. So thank you very much for your attention. I think this is a summary of the key points that I've mentioned, so I won't read them again. If you have any questions on this, I know we can use the chat function. I do need to run to another meeting very quickly here. Please feel free to email, and there's other members of the Earthworks team on the call. So thank you very much for your time.
Thanks, Jim. There's a quick question. Please raise your hand. Let's see in the chat. So I suggest we move on at this point. And I know team members are here. Also, the next talk will be on Earthworks, and that will be by Jingning Huang.
Okay.
Yeah, please just share your screen if you could.
Okay. Can you see my screen?
If you switch to full screen. Okay. We see the presentation mode, so you want to swap.
Oh, okay. Let me see how to switch that.
There's a swap display button. Oh,
no, okay. Let's see. How about now?
Do you see up at the upper in the upper row the swap display button? Did you try pressing that?
Oh, I see. Okay.
Yeah.
Okay, good. Okay. Hi everyone. Thank you for your attention and thanks for the organization. So in this short presentation, I'm going to discuss some of recent work as Jim also briefly mentioned, analyzing the moisture flux transport pattern over West US regions using the CESM coupled with the non-hydrostatic dynamic code that is MPAS. And this is a still primary result. So the key of this work is built upon these non-hydrostatic CSM simulations with the major support from the NSA-funded Earthworks project. First, I'd like to briefly introduce the background and the main questions we'd like to answer for this study. So first, this work is connected to one of our previous work that is focusing on evaluating the CAMPAS performance in precipitation features, and we did the case study over the West US regions. Here are the grid mesh domains that showing the transient scales from the 60 kilometer to 3 kilometer. As you can see here, the 3 kilometer covers the whole West US region and also the adjacent ocean region. So for connect to followed by this evaluation work, we like to understand the large scale moisture flux transport pattern, because that is the key to this precipitation over the West US region. And we'd like to see how the model behaves in terms of the moisture flux transport, and also how that actually linked to the landfalling precipitation. And we compare this model result to the model to the analysis this slide. First, I'd like to show just a overall picture of this mean integrated water vapor transport pattern for the simulations, and also the corresponding result from the magnitude side. And we have 5 West CESMs from the experiment that covers the time from November to March for each West CESM, and for the years from 1999 to 2004, from left to right. And for the first row is the result for the CAM-MPAS, and the second row is for the magnitude analysis result. I'd like to point out that due to these different dynamics over the Northwest and the Southwest coastal regions for these AI-driven precipitations, heavy precipitations. I'd like to focus on separating the analysis for these two different regions. And the wind dynamics shown here is for the near surface average wind pattern. So first let's look at the thermodynamic component for the moisture concentration for these heavy precipitation days. When I say the heavy precipitation days, I'm using the 75 percentile as the threshold to select the heavy the precipitation days above this value. So for Northwest region, I average the region mean precipitation for the land domain, and similar way for California region. And for the heavy precipitation days, it actually accounts for a major precipitation contribution. For Northwest, for these days above 75 percentile, it accounts for about 70% of the total precipitation during this wide seasons from November to March. And for California, that's even higher, which is about 80% of this total precipitation accumulated during the wet season, average over five years. And here, just like brief message shows here is the well-presented moisture concentration over these different heating regions, and with this close match spatial patterns between the campus and the magnitude side. And when we incorporate the wind dynamics together, here shows this integrated water vapor transport. Again, for this heavy precipitation days above 75 percentile threshold. And this, because as I mentioned, like the Northwest region and California region, they are this heavy precipitation days are associated with different types of tracks, AI tracks, and dynamics. As you can see here, like the model actually did a pretty good job when we average we composite the result of all these heavy precipitation days. It has this reasonably spatial distributions for the moisture flux transport pattern, and also the magnitude is pretty close to magnitude. However, we do see some underestimation for the CAM impasse compared to the magnitude side. And also because we have much finer resolution for CAM impasse, which is 3 kilometers versus the 0.5 degree in magnitude. So we do see some finer features in CAM impasse for the moisture transport pattern. But again, we don't have fine resolution seasonal temperature forcings. So it's not that actually fancy over the ocean region. Then we like to further investigate the contribution for the moisture flux transport in terms of the space humidity and wind components. To do this, I'm focusing on the mid-coast regions, that is from the 130 to 140 west degrees, and then I did this latitude and pressure height vertical profile analysis, average over the longitude from 130 to 140 west degree. And again, this first law is the result for the Northwest region, and the second showing the result for California region. And we, if you can take a close look at it, we have the vertical dashed line denotes the latitude bounds roughly for each of these study domain. For the specific humidity, is the moisture profile is generally well captured. But if you look at, but if you really like take a close look at, we can observe this deeper gradient in Km paths, both in the latitude direction and in the vertical direction, which is consistent between the northwest and the California region. And in terms of these wind components, first here is the dominant zonal wind profile. It's similarly as this space humidity, but we actually increase the heat levels here just to want to show the overall picture of the wind, the vertical wind profile, how it looks like in the model and how it compared to the analysis this side. And we did regraded the result for Km paths to the same resolution as the magnitude this side. For so for the northwest region has the top low shores here. We see like the overall jet stream and vertical profile distributions are pretty reasonably captured, but we do see the intensified zonal wind pattern in general in for Km paths for the ARs hitting northwest regions. And for the California region, the profile is generally matching between the Km paths and the reanalysis data, but there is a slightly shift of this Justin location to northward in the model. And when we look at the meridional wind. Meridional wind is relatively secondary compared to the dominant zonal wind pattern, especially over the northwest region, as you can see from the magnitudes here. But over the California region, it still matters significantly, and we do see like the Km path tends to have this southward balance for this heavy pressure is compared to the magnitude analysis. If you look at the bottom row here, and the values almost doubles in the Km path compared to the magnitude analysis. This could affect the impingement angle for the atmosphere, and also it will affect the associated precipitation distribution directly. Here I'm just showing briefly the sea level pressure, the surface pressure anomaly pattern that is average over these heavy pressure days, and this is the anomalies between these heavy pressure days and the mean state that is average over all days of these wet seasons. And the brief message here is that Km path has consistent sea level pressure anomaly pattern compared low surface level pressure anomaly pattern when comparing to the magnitude, and this signal is consistent between northwest and California, but over different central regions here. And for the landfall precipitation, here is just a general picture of the mean precipitation average over this heavy precipitation days in Km path, and how it looks like in magnitude. Of course, the magnitude has much closer resolution, so we're expecting the precipitation is much more smooth over these complex terrains. And given this 3 kilometer fan scale in campus, we have this much improved precipitation features. But that is not the focus. Here, I want to bring your attention to the right 2 panels. Here is showing the relationship between the IVT and the precipitation for different heating regions. For the IVT here, I'm averaging the values over the corresponding cost grid points at different regions, and each dot refers to each heavy pressure index. The brown colors are for the magnitude this side, and the black is for the campus. The general message is like the model has actually captured the envelope of this relationship generally in good consistency with the magnitude. With that, I'd like to summarize this presentation with one of these case studies in the scope of Earthworks. And we are continuing working towards this analysis and also working towards more test cases using CSM coupled with the MPAS non-hydrostatic dynamic core. But for this research, we do see like it's promising to study the IS across scales using this new generation model framework. And we hope that can eventually advance our understanding in a broader scope like of this climate and the wide extremes across scales. Thank you. Thanks for your attention. If you have any questions, feel free to reach out. Thanks.
Thank you. Yeah, this also, we're entering the discussion period. So let's spend maybe the next 15 minutes on questions that we might have for all the speakers here of the second half. And at 12, we transition over into this informal discussion. And that discussion should focus on these aspects. Can we remove some features from the current configuration, the development configuration of the community atmosphere model?
So, Christian, I have sort of an intro slide for the discussion.
Okay, perfect. Yeah.
Sure. Can everybody see that?
Yes, it's
okay.
not full screen.
Let me just. We are. Well, it didn't go to full screen on my side. I'll just go from here. Yeah. So we're going to have after any questions for the speakers, and thank you to all the speakers for excellent presentations. We'll have 4 moderated breakout rooms with Christiana, Cecile Hane, Brian Medeiros, and I as the moderators, plus 2 unmoderated breakout rooms. They'll run for about 10 minutes. And there are some possible topics, but you're welcome to let the discussion go any way it does. For the unmoderated rooms, it would be nice if you named or nominated a rapporteur who could take at least rudimentary notes and send them back to the co-chairs. But other than that, that's all. And then after the breakout rooms, we'll come back, as Christiana said, for kind of a group discussion about the survey that was sent out last month on removing features from CAM. So I guess the first, are there any questions? Any questions that people would like to ask speakers from this session or the last? Christiana, I guess I can't see the chat or if there are hands up.
Yeah, currently not. Yeah, please raise your hand if you would like to ask a question, especially to our speakers from the second half. I actually had a question for the Earthworks team. I hope Rich or others are still available, or if it's come up. I saw that the transition to GPU technologies is partly supported by companies, for example, AMD. And I was wondering whether we are still now dealing with open source code, or is this now proprietary?
Can you hear me?
Yeah.
Yeah, everything about the GPU port is open source. So there's you know, I guess we crossed that issue when we were working with IBM on MPAS-A for the weather company, and that's the way we operate, because it has to be in order to have the community be able to use it.
Okay. And those changes are also going back into the CSM configuration. What's the status on that then?
Well, that's our intent, and we're still we're working on that. For example, we're working with the MPAS core team to get the MPAS 7 die-core with GPU directive markups into CAM. And we're working with PUMAS to ensure that the PUMAS group to ensure the microphysics markups get back in. And we're also doing that with Club, which the DOE has given them funding in order to move to the directives. So our strategy is to work with the code development teams and the science, I guess they call it the science development teams, to make sure that those things are coordinated.
Thank you, Rich. Steve, do you want to make your point, Steve? Steve Goldhaber? Yeah, so Steve just put into the chat that the PUMAS changes. This is a microphysics.
Oh, sorry.
Back into PUMAS. Yeah, Steve, there we are. Can you comment?
I unmuted badly. So yeah, Rich did comment on PUMAS, but the idea is this has been going on for some time. Jean Sun, who's speaking tomorrow's software engineering group meeting, has been working with us to keep those GPU ports up to date with the PUMAS repo, and that's been going very well.
If I could just add a little side comment about that. You know, if you don't do that, it becomes very, very difficult to maintain synchronization with the evolving code, especially in the physics, which is, as everybody probably well knows, it's constantly mutating under scientific activity. So that's a key effort of doing any of these kind of refactoring efforts.
Maybe a final question concerning this GPU technology. You only listed a few, and of course this is your starting point, but is the idea to have a full physics implementation on the GPUs?
Full atmospheric and full ocean implementation, again with MPAS ocean. But yeah, that's the vision, is to do the full offload. And you know, that if you don't do that, then you get you know, AMDAL bottlenecks and stuff like that, as with the data transfers back and forth to GPUs. So we're trying to do that incrementally. The radiation I didn't mention, but the radiation is the idea is to move to RRTMGP, which is baked in directives in it from Robert Pincus, that version of the radiation code. So we're trying to leverage other people's GPU markup work, not just our own.
early experience by DOE has shown that often the increases in speed up are marginal, and this is kind of work by Mark Taylor and others. So yeah, I'm really curious to see in the future, of course, how this turns out for MPAS.
Well, I think, Jensen will be giving a talk tomorrow. He'll show what it does for pumice. And, I could throw numbers around and talk about that, but obviously we wouldn't be doing this if we were not confident we're going to get good speed ups. So.
Okay.
If you have a question for our speakers, maybe let's do one more call. Julio, please raise your hand.
I would say then, if it looks like there are no more questions, why don't we go into the breakout rooms for 10 minutes and then return to talk about the survey and the sort of software management issues that the survey was the result of. So Elizabeth, could you launch the breakout rooms? Oh, here they are. Okay.
We're not randomly being assigned. We have to choose one. Is that the...
Yes, go ahead and choose your favorite moderator. I'm really just joking.
That's probably it. We have about 10 minutes. And if you could, it would be great to see everybody. And it often is a more interactive discussion if you want. So we have a few topics, but it's open-ended, and feel free to suggest. We could, address.
Christian, you're still in the main room?
Oh, I'm still in the main room.
I can send you to your own room if you'd like.
Yeah, please do, because I didn't get an invitation to work on.
There you go.
Oh, thank you.
Okay. So has everybody left the breakout rooms, Elizabeth?
Maybe they just left the meeting.
Mm-hmm.
Yes, I think we were automatically sent back.
Okay. So then I think let's continue the discussion of the survey. I'll share my screen again. So a lot of you probably saw the survey that was sent out several weeks ago on removing features from CAM. The reason for the survey in the first place is that the software engineering, the maintenance burden is becoming unsustainable for our software engineering group. We identified a list of features that we thought might be, candidates for deprecation, and they're listed there. The survey itself, I think the main result of the survey was that there's kind of a lot of interest in retaining SPCAM, driven by the fact that it's being, that it's actively being used by the community in many ways, particularly in machine learning and artificial intelligence parameterization development. So that is I think the kind of the salient result of the survey, that the community really wants to keep SPCAM around, and we'll go into that in a second here. Another less, I would say, less salient, but still significant thread was that, people seem to be willing to let the Eulerian dicore go, but this is going to require development of SCAM, because SCAM right now relies on the existence of the Eulerian dicore for coupling and other things. So someone added this to the slides, that this development will take place later in the year. Okay, but so now let's go and talk about SPCAM. And at this point, if Steve or Cheryl want to jump in and correct me, or anything else, please do. But this is a list that was, a list that we compiled over the last couple of days, listing reasons why SPCAM is hard to maintain. There are two versions of SPCAM. There are, there are copies of physics in each version of SPCAM, including a copy of Club, which apparently is pretty outdated. There are frequent instances where lots of files during pull requests that have to be modified many of the files are in SPCAM. And obviously SPCAM is expensive to run, so that climate validations of SPCAM are not frequent. I think it was mentioned during or right after the talk by Michael, that the last validation that I guess that the group here at NCAR is aware of or involved with was with CSM 1.1.1. So that's an older version of the model. So anyway, The software engineers have been modifying SPCAM to keep it up, keep it passing tests with the current CAM configurations, but we're not sure it's still, producing sensible results with the modifications that have been introduced to the model in the last few years. So I'm going to turn it over now and let Steve or Cheryl, and actually Kevin has his hand up.
Yeah, before maybe we hear from Steve or Cheryl, I just wanted to add that maybe I'm being a little annoying here, but this comparison of 200x CAM for CESM 1.1.1, it's worth acknowledging that the tuning of hypothetical development versions of CAM 7 are, that's not a comparison, right? That it's not 200x anymore because of the cost that's
CAM has gotten slower.
Yeah, right. So, but I think that it's worth mentioning, and I'm being a little bit provocative, right? That each year that goes by that we make CAM more comprehensive and complex, the more in line or the more potential that SPCAM is actually more affordable relatively. It's just a side thought. Now, that's not completely true because, of course, some of the updates that go into the full CAM are needed for parameterizations outside of or within SPCAM on the side. But I think that this comparison of the, in short, I think the statement that SPCAM is expensive, I think, is not a fair comparison when we also consider that we spend a lot of time talking about how we want to go to high resolution, right, which would also.
And we've just increased vertical resolution.
So that's all I wanted to add. Sorry.
Okay. So do Michael, Steve, or Cheryl, I don't want to put people on the spot, but I think you guys are the ones who know these issues the best. So do you have anything that you want to add or correct in what I said, what we need to talk about? Steve, Cheryl and Steve both had their hand up. Go ahead.
And Mike does too. So I want to focus on the infrastructure and not so much on the tuning needed to keep SPCAM going. Mm-hmm. And I probably have been, as the manager of this group, of the software group, I'm probably the one who's been whining the most about how much this is slowing us down. Essentially, we're, CAM is getting, the CAM infrastructure is getting pretty old, and we're spending more and more time just bandaging up things that are happening every time we try to get more science in the model. And SPCAM is one of the areas that, because it hasn't had any real development, it's taking up a lot of time and preventing us from implementing new infrastructure. For instance, Mike in his paper mentions that the CSM load balancing infrastructure is not capable of really handling the kind of focus he wants to put on having different grid cells have different number of super-parameterized cells. I think I'm getting that correct. Let me correct me if I'm wrong, but we have the ability to do that. We just don't have the time to implement it because we're spending all of our time bandaging up the current infrastructure. And that's really what motivated this discussion.
Mm-hmm. So Michael, you had your, you were about to say something, Mike?
Oh, sure. I thought I would just jump in too.
Sure.
I could wait till after Cheryl. I had my hand up after.
Okay.
This.
All right.
Well, I just wanted to kind of emphasize again the second to the last bullet point that the software engineers have been attempting to keep SPCAM current, but we do not know if we have scientifically broken it. And it made me very nervous to find out all of a sudden that it's being used scientifically with the current CAM, because I was the software engineer who put it in originally back probably about 10 years ago. And when we put that in, we ran extensive tests for both of the two versions of SPCAM, got the scientists to sign off on it, and they said, great, this is perfect. Yeah, let's put it out. And that's what we did. But since then, I'm not sure anybody has done that. And it makes me nervous. You know, for example, with this new NDrop PR that is currently out there, 5 files that are SPCAM files are going to be modified. We think we're doing it right, but we haven't, you know, there's not going to be a scientific run done. So, you know, that's my biggest concern, is that we're not sure that we're keeping it, that we're not breaking things.
Yeah, these are super important concerns, and it's interesting to hear about the baggage that comes along with maintaining SPCAM, and that slows the pace of regular model development, which is news to me, but I understand.
So given the community interest in SPCAM, I think what I'd like to do, and we discussed this a little bit yesterday, is move it from the baggage cart to a place where development can happen, and it can both progress and lower the burden on core CAM software engineering. One possibility is finding funding to help with the process of maintaining SPCAM. And I noticed that LEAP is hiring an integration engineer, and this is exactly the kind of thing that is an integration problem. And somebody yesterday, I think was it Jesse, suggested we could actually move SPCAM to become an external like Puma's, where it's easier to develop, and the modularization actually lowers the software engineering burden on both sides. And there's, I think, a discussion to be had to try to work with the community, now that we've been made aware of the fact that it's being actively used, to try to bring it forward. So the opposite of deleting it from CAM, essentially.
Mm-hmm.
But that's, we're gonna need some outside help. Rich? I don't know why I'm calling on Rich, but
yeah, go ahead, Steve. You take over. That's fine.
I just wanted a chance to stop talking, so I'm helping Rich get me out of this hole here. Yeah.
Can I ask Mike, who is is Murat still actively developing SAM, or are there other people? If we were to say we want a new version of SAM, what would happen?
Yeah, so there's been a lot of developments, right? Murat has sort of moved on to GSAM, and that lives externally of SPCAM. The biggest MMF development is happening inside the DOE, the E3SM MMF project. So as part of the exascale computing project, a whole new pot of money emerged that was the only GPU portable target. And there's been a ton of development in that code base, which is open source, but I think it would be like oil and water. My fear is that that code, because it's trying to become architecture agnostic, will become inscrutable to the scientist. And you know, there's a C++ port of SAM called PAM being developed at ORNL that's going to have all sorts of wonderful features like we know and things that you would like in an LES, but it's going to be pretty difficult to read and pretty difficult for a grad student to do any experiments with. And the part of me that thinks it'd be really important to keep a version of SAM alive inside CSM is the part of me that thinks grad students should be able to read cloud resolving code and muck with it and interfere with it and do experiments with it.
Yeah, I agree.
But yeah, in terms of the people involved, that's what I'm aware of.
Yeah, that sounds like one of those areas where, you know, we struggle with this, trying to make code performant, but also keep it readable, because, you know, that's part of what scientists need to be able to do, is to understand what they're running. So this is why, and there's going to be a talk on this tomorrow morning, we want to move towards GPU porting. Right now we're using OpenACC. We would like to move to the new OpenMP, which unlike OpenACC, it supports more architectures, different types of GPUs, but also other types of accelerators like FPGAs and stuff that are coming up that the OpenMP standard is now capable of handling. So that is sort of the opposite approach that DOE is taking with, I'm spacing the name of their tool now. It looks like C++, but it's not C++, and it turns into either C++ or some GPU code. Yackle? No, it's something else.
Cocos?
Cocos, thank you. Yeah. I don't know if the SAM is being written in Cocos or whatever Yackle is. Yet another crazy language. I don't know what it stands for. But Cocos is deceptively looks like C++, but isn't really.
There's lots to respond to there. I mean, yeah, so the MMF team at DOE has moved to this Yackle thing that's a backend that can be C++ and run on GPUs or on AMD machines, and things are changing underfoot with architecture. So there's a lot of appeal to trying to bring that into CSM, perhaps if you want to do something architecture agnostic without reinventing the wheel, and that's a strategy that could be considered, but it's a big resource.
Well, that's why OpenMP, which is also, because it's a consortium, it's very much architecture agnostic. And it took them years to develop this new version. OpenACC was a sort of a stopgap, and it always intended to come back into OpenMP, where all the vendors now are supporting this new version. So if you want to run on Intel accelerators or other vendors, not just say NVIDIA, the new OpenMP is the way to go. And it doesn't really hurt the readability of your code much. I think it'll be relatively easy to convert from our current OpenACC implementation to OpenMP once that's ready to run on, say, directional.
Could I ask another question?
Please.
So I've heard, kind of the self-contained aspect of SBCam being, I've heard it described both as an advantage and a disadvantage. Michael this morning said, yeah, well, SBCam is a wrapper and it calls its own, whatever parameterizations it needs, it calls. It has them internally and uses them. And then I've also heard that it's a burden that we're maintaining several versions of club, the radiation. So which is it? Is it better to have SBCam sort of in charge of its own suite of parameterizations, or does that increase or decrease the level or the effort required to maintain it?
In the current infrastructure, that's the source of the increase of work.
What I didn't understand.
The fact that there's multiple copies of stuff is the reason. I think, it's a little hard to judge without doing a detailed analysis, but the reason we're modifying so many things inside of SBCam is because there's copies of older parameterizations inside of it that anytime we update the master version, we have to update the SBCam versions as well. If SBCam itself became more modernized and modularized, then a lot of those problems would go away.
So
but
you
that
would
takes,
prefer...
there's a big bump effort to do that. So there's all kinds of ways of getting to a better place than we are now. I think, the ultimate would be to have, an engineer stare at it and say, okay, here's a way so that it doesn't have to be one thing. Right now, it's two things inside of CAM, right? It's basically you run one of the two microphysics versions and you have two different versions of SBCam, but that in itself is limiting, and SBCam is not really amenable to growing out of that box. Somebody has to put a lot of effort in. And if we really want people to experiment with it and see what we can do with this technology, with this science, because it's not just Mike's talk, but stuff yesterday showed a lot of promise. If we really want to be able to realize that promise, I think we have to open up the SBCam box and bring it up to bring it up to par, but that takes significant resources at the front end.
So, I mean, it seems clear to me that some, you know, there needs to be some kind of strategy, and we're not gonna fix things here today. How should we go ahead?
I think we need a connection to the community that's doing this so that we can start talking about it. I'm a big fan of co-design, where we actually meet with people before they go do something and figure out a good way to do it. And in this case, LEAP seems to be ready to fire up a bunch of work. And if we could get involved and help guide some of that work, we could get there from here and in a sustainable fashion, but also in a fashion that opens it up for more flexible research, which sounds like it's needed.
Okay. I put up some bullet points from Cheryl.
This is just a sort of I think a straw man of like, hey, we could do this as an idea. And this is essentially replicating the model we're using with Club, with Pumas, to some extent with some of the other externals that we have. It's the goal for trying to pull chemistry out of CAM and to make it more modular so that chemistry can become more flexible and come into CAM in a modular fashion as opposed to the way it's plugged in now. But that process as we go forward is going to keep hitting SPCAM over and over again and just trying to figure out how we're going to get all that work done and meet any kind of deadline for, you know, a CMIP class model, a CSM3 release. It's really starting to drag us down. And so I think we just got to get smart, work together and come up with a solution that gets us all to a better place. I do think it's possible, especially with a little bit of funding, possibly from LEAP.
So the key thing is to make some kind of connection with the LEAP hire
and the LEAP team and other research efforts out there, so that nobody's left off the table. And you know, just glancing at Mike's paper, I see, well, okay, we should go ahead and implement. You know, we should have the target implementing the load balancing that would basically balance the physics regardless, you know, so essentially you would specify how much work is going on in a grid cell, and that would essentially be proportional to the number of MMF inside of each grid cell, which is variable, and automatically load balance that. Why not? We can do that. All right. Mike, you have your hands up. I don't know if you're gonna.
Yeah, I think I do think it's the beginning of a longer conversation, right? I feel a little self-conscious that I've like projected my myopic interest in SPCAM on really busy CSM developers. You know, and you know, LEAP is very interested. There is real important work that can be done for prototyping machine learning models, but you know, that's different than maintaining it as a feature that you know is there with the model. I think some market research is needed to understand in the wider CSM community how important people feel explicit convection is. It is the only path I know of to have it in a way that doesn't break the computational bank, that doesn't require like a leadership class allocation that you can, especially when you can regionalize it. And so I do feel like there's potential value there to the impacts part of CSM and to the people just with niche dynamical interests that want to understand the feedbacks between explicit convection in one part of the system and broader climate dynamics elsewhere, in which case having it maintained adjacent to really modern and cutting edge state-of-the-art CSM everything is like important. But I don't know if that market is out there or not in the CSM usership beyond LEAP. If it were, it would sort of seem to motivate, I don't know how we raise the funds through CLD or otherwise to do the strategizing the right way and think about the best successor to what's in there now that would not create lots of work for people, or whether it's an external or otherwise. I don't know how those are maintained with Club, the externals.
I don't know who maybe it didn't come through, but the reason SPCAM kickstarted this discussion is because the overwhelming number of responses to the survey was about SPCAM. So it really feels like there's a market out there. It feels like there's a lot, which is why, you know, I'm trying to, you know, pivot from we need to get rid of it to we need to figure out how to do this right. You know, in order to support the community, which is clearly out there. And yeah, so this isn't, sorry, Mike, not about you.
Yeah. And I'll let Brian talk, but I just want to say, yeah, that we had at least twice the number of responses that we normally get to these sorts of surveys. Imploring us not to eliminate SPCAM.
Which I think it basically brings up the point that I was about to make, which is that if these people don't have CESM's version of SPCAM to go to, they have nowhere else to go to. I don't think that there's anywhere. I mean, maybe the DOE version is somewhat accessible, but it's, I think, more expensive and harder to use than our version of SPCAM. And so I think that we have a tool here that's got at least a small community of interest and a lot of interesting applications that I think we want to support. So I don't know if anybody else is going to support that community, so we should.
Yeah, and we do have to figure out the funding problem because, you know, another example is SCAM, which is immensely popular and incredibly valuable. Well, a lot of people would say you can't really do physics development without it. And yet we've been unable to get funding to really renovate it and get it off the Eilerian Dicor and make a lot of improvements. I think we have some hope for next year. You know, we've tried to put something together inside the app section. Rich can talk more about that, but you know, it's a hard thing, and so getting the community together and trying to figure out how we can fund this to make a modern super-parameterized CAM that we can actually, you know, be happy with and proud of, as opposed to dragging along something that hasn't been really kept up to date.
Maybe I want to just add a couple of thoughts. So I think there is a lot to do, actually, if we decide to keep the SP version. For example, we move to the new grid configuration, the vertical. This must be looked at, you know, also talking of scientifically validated versions. We have these other dicores coming on board, which are no longer on the lat long grid. I guess, Mike, you indicated that spectral element has been used in your group, but we really don't know whether there's a scientific basis, you know, whether it's stable, it's the top of the atmosphere radiation balance is there. So I'm not certain how much you look at this, Mike, but I think there are big questions like that. We heard about the load balancing. We never have seen, at least to my knowledge, also any attempt to use SPCAM with CAM6 physical parameterizations, because maybe that's this concept that they are all embedded, the old club version. So all these aspects should be addressed. And of course, LEAP would be a great, could make a great contribution. But again, as Mike mentioned, maybe not, they probably don't want to be the owner of SPCAM. Also, I'm concerned that SAM, the underlying cloud resolving model, is basically no longer maintained. There's no owner of the cloud resolving model, and DOE has moved on to build their own version of a cloud resolving model. So they are abandoning the SAM version in the future. So all these considerations that we should look at.
Just to respond quickly to that, yeah, I think opening a line of comm with the DOE group would be really helpful towards this visioning, because there has been a lot of vertical resolution sensitivity testing inside that project, as well as Dicor testing, and there have been some decisions made to upgrade the physics to P3 and shock inside PAM, and And it is possible, to Colin's comment, that there might be some opportunity that the engineers would recognize to leverage that to make it an external. I know at the beginning of that project, everyone was admiring Cheryl's implementation of SP and CSM 1.1 as a basis for their starting point, and maybe there's a reciprocation there that could happen. But you know, and the architecture agnostic aspects of PEM might be quite strategic for a future. I don't know the format of Duresho, but that conversation will be interesting to see. I think that the DOE project seems to prioritize these massive simulations that just have to run on 1,000 nodes of insight, no matter what the science context is there. So they're probably less interested in load balancing, niche regionalized resolution for the grassroots community, and may have overlooked some of the load balancing and regionalization opportunities that, that CSM's more diverse user base could benefit from. So maybe there's like a middle ground strategy there between the two code bases that could really fill a niche. But this all sounds like a lot of work, and funding and personnel is probably the limiting factor. And I still am not clear on like how one approaches CLD or who for. It's obviously asking too much of, you know, core resources to do all of that visioning and implementation. And how were things funded for the original SP implementation in CSM? I know that was a legacy of CMAP, but I don't know how it was achieved logistically.
So my funding came from Dave Randall's group at an SPCAM. And so my funding came from his group somehow. And I'm not sure if Ming-Wai Wang also had some funds, but I know Dave Randall was the main, he had a project and his funding was what supported my development work.
Judith, your hand's up.
Yeah, I just wanted to sort of comment. I think it would be very valuable, and we should keep SPCAM and think about how to implement it. But one of the things is that it competes with other software engineering efforts, for example, CCPP. And so I think that's something to be considered, which is another very valuable unification effort, with the idea to be able to try more things with less effort, because you have an interface and you have sort of rules and a protocol, and you can flip, for example, parameterizations. So I think while we all agree that keeping SPCAM should be a priority, it's like, how does it relate to something like CCPP?
So I'm going to propose that we sort of adjourn for now and continue the discussion in another forum. I don't know what forum that would be. I'm thinking of you know, having a meeting between Mike and some of us here sometime in the next few weeks, after perhaps somebody here has talked with Dave Lawrence about the leap hire. Does that sound like a good path at this point?
It does, but can I ask? There are some questions in the chat about the possibility of using of DOE and us using the same externals and leveraging all the work that Walter's done to their cloud resolving model. If that's not feasible to marriage our two works together, then okay. But if it is, then maybe we should include Walter in these conversations.
Okay. Good.
Yeah, that's a great idea. He'll know the details And he's also, yeah, so that, yeah, he'd be really good to work with. I mean, I worked with Walter before. Yeah,
okay.
I just wanted to add a very quick comment. My understanding with Leap in the integration engineer is that they're mainly going to work on this interface between how to get something that is learned in Python back into Fortran code. And so it's sort of a very different.
Okay, maybe it will be a fruitless effort, but it's still worth a discussion with Dave Lawrence, I think.
Well, and also possibly with Galen, because you know, we've had a problem in the past, and we even have a problem with CSM Unity of this. You know, the number of scientists wanting to contribute stuff relative to the number of software engineers who are available to put it in. There's a very large discrepancy in numbers, and what I saw yesterday was a whole lot of postdocs and one software engineer, and I just don't know how to make that's going to work. Maybe it's not too late to improve things.
Okay. All right. I really think we're going to have to wrap up soon. Why don't Leo?
I'd love to hear from Leo at least.
Yeah. Hi, everyone. I was just going to follow up real briefly on Cheryl Craig's comment and really take this back to CMAP. Julio, I wonder whether it might not be worth a discussion with Eric DeWeaver at NSF. There's a general issue that the science and technology centers are doing really important things, and they have legacies like SPCAM. LEAP is likely to have some, Earthworks possibly going forward. And look into the possibility of some dedicated funding to keep these very important legacy projects that involve the CESM going, that really are stretching beyond, you know, the capabilities of NCAR with current resources to do. I don't know what will happen, but you know, the NSF has made an enormous investment. Mike's made a really strong case how important the SPCAM investment was. To let those falter because of a lack of resource for something that's, you know, in the overall scheme of things, kind of minor, would seem sort of tragic. So, I mean, I don't know if anything will happen. If I were back on, you know, in my days as CAB chair, I'd be putting this on the agenda for the CAB as something to talk to NSF about. But I would encourage that discussion. What I've been hearing is really compelling about these legacies coming out of the science and technology centers, and they're likely to keep coming. And it would really be wonderful if CSM could be a part of that, but you need to be resourced.
Okay, so yeah, I think bringing it up to the SSC, CAB, and Eric is also something that, that
absolutely
will be done. Yep. Okay, so why don't we adjourn for now? There's another session starting in 10 minutes. So I'll be in touch with Mike and others here, and we'll together we'll figure out where to go next. So
thanks, everybody.
I'll leave it vague for now, but we'll do some. Thank you. It's been very, very useful.